I don't even know what I'm going to say. So it'll be fine. Just go and chat. Yeah. All right. Good morning. Good morning, everyone. How are we feeling this morning? Everyone super awake? Yeah, there's a higher level of energy in this room than I expected. I feel like there's a higher level of energy from you guys than I am currently feeling. I hope everyone had a wonderful evening last night and had some good food and some good conversations and some beers and whatever you need, or sleep. Sleep was good. Today we have another wonderfully packed schedule for you. We're addressing sort of a wider range of transparency topics today after yesterday's quite CT heavy day. So it should be good. I don't actually have that much to tell you this morning, so without further ado, we'll just get started on our first session, which is hardware-backed approaches. And I'm going to introduce Fredrik to start us off.
All right, let's see. Good morning, everyone. That's sufficiently light. I'm sure I will be thoroughly awake by the end of this session. Okay, so I'm going to talk about a HSM prototype that we have built. But first, short introduction. My name is Fredrik Strömberg. I'm involved in these companies. I'm not going to go into detail, but in short order, they are Mullvad VPN, which does a VPN service, and we also have a browser based on Tor browser. There's Telitis, which does open source hardware. There's Glasklar Technique that does SIGSUM, the transparency log, system transparency, which is a combination of remote attestation, reproducible builds, and transparency logging. On paper, right now it's a glorified bootloader, but we keep getting distracted building transparency logs and hardware. And now we also run the Debian snapshot service, which is a few hundred terabyte disk array with a bunch of Debian packages. And there's Carl Stainton Privacy Lab AB, which does traffic analysis defense against AI-based classifiers. So we started 15 years ago, and eventually we became obsessed with, I'm talking about Mullvad here, obsessed with what trust assumptions do our users have to, what do they have to be vulnerable to? And we ended up with system transparency and trying to reduce the trust assumptions and make them more explicit. And then we realized that for system transparency, we needed a transparency log. And we started building one. And sometime later, Telitis was founded, and we announced the T-key. And earlier this fall, we announced the existence of an HSM prototype, which I've dreamt about building for many years, but it's felt a bit too ambitious until now. Right here, unfortunately, this is the wrong, this is an earlier version. We now have an actual PCB, which is not made out of super glue and silver tape. On the left-hand side, you have the Telitis T-key, which you can think of as a trusted execution environment on a USB stick. You can also think of it as a computer that does measured boot and uses that as a key derivation function. It is also the most open source hardware, firmware, and hardware USB security key that I know of. The PCB design, the schematics are made in KiCad. They are on GitHub. Same thing with the HDL, because there's an FPGA on there. Same thing with the firmware. And we reverse engineered the programming and locking protocol for the on-die NVCM OTP memory, so you can program it and lock it with open tooling as well. And of course, we use the uses toolchain with NextPNR, so you can synthesize your Verilog all the way and put it on the ICE40. And on the right-hand side is our HSM prototype. What is an HSM? Well, basically, It's like a YubiKey, except or a T-key, except it's more powerful. And there's usually also a notion of physical security and tamper resistance or tamper detection or tamper reaction. So you have this computer. It holds keys that are very important to you, perhaps some type of signing key. You do operations using those keys, and you have tamper sensors like pressure or temperature or vibration or GPS position or other things. The HSM market today is mostly an oligopoly consisting of unverifiable proprietary black boxes. And wouldn't it be nice if instead it was slightly more open? So that's what we're trying to do. These are my favorite. This is my sort of design philosophy. I've been interested in cybersecurity since I was 12, and I come from a family of inventors, so I like thinking about creativity and strategy and in my case, cybersecurity at the same time. And I like to decompose things until you find the atoms, right? So in physics, if you can find the underlying fundamentals, it makes it a lot easier to reason about nature. And I think the same goes for cybersecurity. The question is, which design primitives are the most long-lived, the most fundamental, give you the most bang for the buck. Because, as we all know, more and more complex systems are inevitable. If you want more features, you need more logic gates or more machine instructions. And so you have this graph where with increasing complexity, you have the expected and intended behavior of the system, and you have the actual and surprising behavior of the system, and the delta between these two lines is your attack surface. And so that begs the question, with more and more complex systems, with more logic gates, higher clock frequency, more lines of code, how do we keep these two lines together so that the intended and expected behavior and the actual behavior of the system are the same, more or less? And I like hardware defenses, because hardware defenses, they set the rules for software. So software can't do things that the hardware doesn't allow it to do. Cryptographic defenses are nice because they allow us to create security margins that we can express in terms of how many exajoules of energy, how many Dyson spheres of ideal computronium, and how many millennia do we need to crack this one instance of AES. And if you knit things together, symmetric ciphers, forward secrecy, integrity protection, authentication, then you get a new concept. Secure communication channels. It's the same thing with transparency logs, right? We just knit together Merkle trees, hashes, and public key crypto, and then we get transparency logs. So those two are very nice. Obviously, restricting the state space is also a nice thing to do. I think we should think about software as the purpose of software is to converge the reachable state space of the running system on the set of behaviors that you care about and not the set of behaviors that the attacker cares about. If we had infinite money, we could just produce hardware that did exactly the thing we wanted, but alas, we have to amortize the cost by buying things that are chips that are programmable. Software is used to make it less programmable, or we have a boot chain and we want it to be a web server or a WireGuard server and not part of a botnet, for instance. Distributing trust assumptions is also nice. You can do this with multi-signature schemes. You can do this with multiple branch instructions in a row that give you some amount of glitching protection, or perhaps you have cores running in lockstep. And of course, you want the specifications and the implementation and the supply chain to be as available and understandable to you as possible. The HSM that we are building builds on the T-key, which I described before, the USB Armory, which is a fantastic device, which I'm very grateful that Andrea and his colleagues started working on many years ago. It runs Tamago, which is a fork of Go, that you run bare metal on the device, and now you can also run it on x86. You can even run it as a bootloader or in UEFI, the UEFI context. And then we have the Cryptic HSM, which is a project created by, among others, Joachim Strömbergsson, which is and Linus Norberg, who is also here, and some other people. It's a collection of primitives, open source hardware that you can use to build, for instance, an HSM. I believe OpenTitan uses some of Cryptic's cores. We certainly depend on a lot of their work, and they also have designs, things related to like how do you build a good TRNG and things like that. So we tried to take the best ideas from these three projects and then bunch them together in something new. And it looks like this. The three critical chips are the NXP IMX6, which is an ARM core running Tamago, that's bare metal Go. We have the ICE40, which is the same FPGA that we use for the Tiki. It runs 32-bit RISC-V core and some other things. Then we have the ECP5, which is a larger FPGA, also from Lattice. It has around 80,000 logic cells, so much bigger than the ICE40's 5,000 logic cells. And that one also runs a Tiki design, but with additional cryptographic accelerators in the memory map. And then there's some RAM and some micro SD slots, and the current prototype doesn't have any tamper sensors, but as you can see, that's the idea. Okay, and then there's SIGSUM. Most of you, I mean, yeah, I'm not gonna. So, as probably all of you know already, but I'll just give a short summary. So, in a transparency log context, we have a few actors. In a transparency log with distributed trust assumptions, we have additional actors or components. There's the log, of course. There's the, or without the transparency log, you have the signer and the user, right? And so you get signatures that give you authenticity. If you have a transparency log as part of your client's trust policy, you get signatures that give you both authenticity and discoverability. That's how I think about it. And of course, that requires requires the signer to send, in the case of SIGSUM, a signed checksum to the log. And we have witnesses that witness the log and make sure it's consistent from their network vantage points. The log provides a proof, a cosigned proof to the signer, and the signer sends this proof to the user as part of the usual software release process or whatever. And then, crucially, as Filippo likes to remind us, there is the monitor, hopefully, that monitors the log and discovers key compromise or key misuse. Let's see. I'm doing it really well on time. Is that right? Do I have 7.5 minutes left? Yeah? Okay. Wow. Whoa. I mean, did I just ramble through that thing? Was it coherent to you? Okay, fantastic. I'm sure I woke up, maybe a bit later than the rest of you. I don't know. In any case, okay. So we're gonna do a demo. The demo is not going to include everything that we actually have. So if you want to see the HSM prototype up close, we have a few with us. I also have a bunch of my colleagues here that are more than happy to tell you all about the technical details. And of course, there's the hackathon room on the other side, where some of us will sit with our laptops and do things with this prototype, and we can show you. Basically, Actually, I think I'm gonna tell you about our future plans, and then I'm gonna go back and describe the HSM a bit more, and then my colleague will come up here and do a demo. Okay, so basically our future plans are to productize this prototype. Again, it's currently a prototype. We don't know when it will be done, and it does have some limitations, but hopefully it will be the most open source hardware HSM there is, which is fun in itself. And the engineering challenge is to make it fairly secure against physical attackers don't seem insurmountable, at least if you in terms of getting it NIST FIPS 140-2 certified, or at least have the equivalent type of security. So that's interesting. Separately from this, we also have plans to do open source silicon, which has nothing to do with transparency logs, but it does have something to do with transparency. The short version is that thanks to Google and Tim Ansell and Skywater and eFabless, there was a way to do tapeouts, open source silicon tapeouts using tiny tapeout, and you go through eFabless as an MPW service, and Skywater would provide you a tapeout. eFabless unfortunately shut down the company earlier this year, but now there's a new MPW service by Tim Ansell. So if you go to wafer.space, you can buy things from the GlobalFoundries 180 MCU process. And the reason you will be able to do that is because we are funding Tiny Tapeout to port their tooling flow from Skywater to GF180 MCU. And what's also exciting is that this will probably, that PDK and that tooling will probably, and that process will probably allow us to go all the way down to, I think, 55 nanometers, because it's the same equipment. So if you like open source silicon, check out Tiny Tapeout and wafer.space, and I'm more than happy to preach about those things as well. Okay, so what is running on this thing? We have the host computer, talking to the IMX6, running Tamago. The IMX6 in turn, I'm going to describe things as we envision them, and we have plans to change this, but the idea is that not only do you measure the software, not only does the firmware measure the software that you put onto the HSM, a thing that differs between the HSM and the T-key is that with the HSM, we also intend you to be able to measure the bit stream. So the ICE40, the IMX6 sends a bit stream to the ICE40. The ICE40 configures the ECP5, and thus you can have not only measured boot, but also measured hardware, which is fun. And the idea is then that you have the cryptographic key material in the ECP5. I'm sure all of you have a lot of questions about the security of those buses and so on. And yes, there are limitations, and yes, there are some better and worse solutions to those limitations. But that's the gist of it. So measured hardware is fun. Okay, now I only have 2 minutes left. Shall we do a demo? It's a very short demo, but nevertheless, it's fun. Okay.
Hi, everybody. Can you hear me? My name is Daniel. I'm Fredrik's colleague then, obviously. So, yeah, we're going to do just a brief demo to show that something actually works here, okay? So, and just so you know, we sort of hacked this demo together yesterday during the breakout session, so fingers crossed. But first, a more recent picture of the hardware then. We also have it here, and you can look at it on the breakout session later. But it's a credit card-sized PCB, with a bunch of ICs on it, as Fredrik mentioned. We got the IMX6 sort of facing the terrifying world, providing us with different interfaces that we can use. And as Fredrik mentioned as well, usually in the T-key sense, we have 2 applications running, one on the host, which could be a server or a computer or whatever, and something running on the T-key. For this instance, then, the HSM can do all of that. So it's running both those applications, more or less. So in here, we have a time ago instance running on the THSM right here. And it provides us with a network interface, and we can simply do SSH to get into it. And we get a lot of different commands we can do. Are you able to read this? Yeah, sort of. So we can talk to the FPGAs beneath the IMX6 then. We can just ask it for the UDI or the name of the FPGAs running there. And it says something about TK1 and the MKDF version 5. Sounds great. But we can also then interface with sort of the secret stuff down there, like the encryption keys and stuff like that. So we can type T-key and sign, and we can sign something like, TDS 2025 or whatever. And it will now interface with the FPGA, load an app right now. That might not be how it's done later, but we get something back at least. And I guess that's the gist of it.
Yeah.
We have more applications. Oh, thank you. We figured, what is the conference without hardware on stage, right? Yeah. But we have, as Fredrik mentioned as well, we have another demo as well that's tying more to transparency logging, but let's do that one in the breakout session later if anyone is interested.
Yeah, I could actually.
Great.
Yeah, thank you. Awesome. So I'll. Before we end, I'm just gonna give a short description of that. So you can think of it. So in terms of transparency systems, what can you use an HSM for? And I roughly see 3 possible use cases or three applications. One is that you protect the 4. You can protect the signer's key, obviously. You can protect the logs key, or you can protect the witness's key. And you can also create an app that only signs things if they are already transparency logged, which I think is quite an interesting way of adopting transparency systems, because as I'm sure you've all thought about, if you want discoverability, the client has to fail closed, right? It can't opportunistically say, oh, there's no inclusion proof today. Well, I guess it's fine anyway. So the client has to fail closed, which means you need long-term reliably available logs and witnesses for your trust policy. And then you have use cases where you're not going to be able to have a trust policy that includes these things, because maybe you're using, I don't know, Intel BootGuard or use UEFI Secure Boot, which only supports RSA. So what you can do in that case is you protect your RSA key on the HSM side, and where the HSM doesn't sign any hash, you send it, it only signs hashes that are already in a log. That's a nice way of gradually having organizations gradually adopt transparency logs without having to mess with the trust policy on the client side. So those are just 3 things that we're building. We have a bare metal C implementation of what I just described. I believe it's 80 kilobytes, including all the ECC stuff, so it's still a bit big. But so we can talk more about that offline later. All right, thank you all for listening.
Thank you, Fredrik. Does anyone have any questions?
Yeah, great demo. And in the direction of productizing this HSM, what are the major functionality to be in par with like Utimaco and Thales? And the second question, what is the current status or plans for supporting post-quantum algorithms?
Good questions. So on the first one, we have a lot of work left. I mean, the thing is not going up in smoke. It runs things. We have done, we're running Tamago. We're running things on both FPGAs. But before we start selling it and telling people that you can use it for production use cases, there's a lot of things left to do. The PCB is also just a prototype. I expect that will. I mean, one thing we haven't delved deeply into yet is what tamper sensors do we want? What type of epoxy are we going to use? Are we going to have a metal mesh? Are we going to encase the thing in something? Perhaps tungsten carbide? There are a lot of questions that need to be answered. And regarding post-quantum primitives, we certainly want to do that, and we're well aware of the need, but we haven't gotten there yet. Yeah. More questions?
Cheers. Yeah, thanks. Thanks for a great talk. I was just curious, and maybe you actually mentioned this, but will the HSM firmware be open sourced as well?
Yes, of course. So
great.
Just like the T-key, the HSM's schematic and PCB design are made in KiCad, and we'll be open sourcing that. Same thing with all of the HDL running on the FPGAs, and same thing with all of the firmware and all of the applications. So the entire thing, except for the ASIC designs, which we don't have access to, obviously, will be open source. And in all cases where it's possible, it will be BSD licensed.
Yeah. Nice. Thanks.
My goal was to keep you busy, so I actually have a couple questions. The first question is, have you thought about how you might use T-logs to be able to measure or capture state of the hardware at the same time, not just the hash, only incorporate when, but that same transaction could cover both in theory, which would make that more guarantees about that operation external to the HSM. That was something that you can't get out of an HSM today. The second thought, kind of in the same spirit, is what is the performance overhead of that logging exercise? The sort of the third corollary is like what the TPS expectations you have for the algorithms that you're supporting.
All right. So thank you, Ryan. Regarding the first question, I'm not sure I understood exactly what you were asking. So we can let's take that. Yeah.
Secure boot and
okay.
The PCR equivalent, sort of.
Okay. Yeah. So the we're gonna try to make the ICE40 and the ECP5 running 32-bit RISC-V soft cores. They are doing unconditional measured boot using the DICE approach, and I believe we can make the IMX6 do the same thing, but we haven't done that yet. And when you have once you have that, all you need is persistent storage, and then you can make that into verified boot. And then you also have the flexibility of describing whatever trust policy you want. So we definitely want to boot as much of it as possible with M of n signatures, and then signatures for reproducibility, and then discoverable signatures, and so on. So absolutely. The third question, TPS. No idea. We don't know yet. And the second, overhead. We don't have right now, but we will have eDDSA accelerators on ECP5. So that should be nice. The overhead for T-log verification on the T-key, however, is quite substantial. It takes about 15 seconds. Then again, it's a very open and tiny device, and you can audit the entire thing in not that much time because it's only 5,000 LCs. So, okay.
Are you considering having polynomial operation accelerators also, so we can have post-quantum cryptography on those devices?
We will definitely have post-quantum support eventually, and I expect that some of that will be accelerated in hardware.
Right, I think I'm going to stop it there so we can move on to the next talk. A big hand for Frederick again.
Great, thank you.
And I also want to say that Frederick is actually the one we have to thank for this whole event. He is Mr. Glasklar. He is our host and has contributed a lot to this event. So a big round of applause for Frederick for everything he's done for that. Of course, thank you. Okay, so next we have Adit, who's going to come and talk to us about confidential computing, I think.
Hi, good morning. My name is Adit, and I will be talking about confidential computing, trusted computing in the cloud. As a brief agenda, I'll be starting with some of the background, then talking about how this technology actually works, and then finally applying this technology to the transparency ecosystem with witnessing. So back in 2015, Intel released what they call their secure guard extensions and this concept of secure enclaves, where their goal was to be able to allow applications to run sensitive code and use sensitive data on untrusted platforms through a combination of hardware and software features. These secure enclaves were encrypt the memory within the enclave and isolate that data from the host operating system, such that even if somebody has root access on the host operating system, they're unable to access the data within that enclave. So in 2017, Signal was an early user of this technology on the server side. Signal has this feature where you can look up your contacts and check if they are Signal users. But the search space here is pretty small, right? And so it's hard to do this in a privacy-preserving manner. And so what Signal clients do is that they establish a connection to a secure enclave running within servers on Signal's cloud servers. And the enclave is able to provide an attestation, which is a signature over the initial state and this code that's running within that enclave. Once the client verifies the signature and this attestation, the client will only then send over the user's contact data. So with SGX and this initial technology, the access to the data was pretty isolated, only to the application. But this provides a lot of overhead, right? The application needs to tie in with secure enclaves. The developer needs to architecture their application with this use case in mind. And so Intel and AMD came up with this idea of confidential virtual machines, where we increase the trust space to include the guest operating system as well. But this makes it much easier to transfer traditional applications into this confidential space without having to make modifications. So both Intel and AMD have their own implementation of this technology. That being said, I'm going to be focusing more specifically on how AMD does it. And they are broadly similar. So the primary job of confidential computing technology is to encrypt the memory in order to isolate it from the host. When a hypervisor wants to create a virtual machine, it will first talk to AMD's secure processor. And this secure processor is an ARM Cortex-4 chip, a microcontroller running on the CPU itself, but separate from the x86 cores. This secure processor generates encryption keys and ensures that the encryption keys never leave the CPU. It feeds this encryption key into a hardware AES engine that sits between the actual x86 cores and the RAM. When data comes into the CPU, it'll decrypt it before feeding it into the cores, and then as data exits the core, it'll encrypt it before putting it back into main memory. So then another really useful property, right, is to be able to prove and provide proof to a remote party of what software is actually running within this encrypted space. And this process is called attestation. This is a guest-initiated operation, right, that the VM does, and this is independent of the actual cloud provider, right? This process is the same across whatever infrastructure provider you're using. The virtual machine requests an attestation from the secure processor, and the secure processor performs a bunch of checks, and it'll sign a digest over the initial state of the virtual machine. And this is also why it is really important to have the isolation that memory encryption provides. Without having isolation, once you provide an attestation, the host could go and modify what is running in the VM. And so it's not really a useful property to have without the isolation. The virtual machine will then send this report over to a remote party that can verify this, and then it can send over sensitive data such as signing keys or user data. One really fun note here is that this entire system is also just based on PKI. AMD embeds a certificate into the CPU during manufacturing. And this is actually just a standard PKI cert chained up to AMD's root of trust that the remote party can query and get CRLs for, and then use standard X59 tools to validate. So it's important to really look at the threat model here. This is the table of contents of the Wikipedia page of SGX, and 90% of it is dedicated to vulnerabilities. So yeah, it's like we really have to pay attention to exactly what we're trying to protect against here. So this is a select list of threats that are taken from AMD's SEV S&P white paper, which is AMD's latest generation of this technology. So to start with, there is no availability guaranteed by this technology. The hypervisor is always able to shut off the VM and not schedule it and not schedule any CPU time. That being said, we do protect the memory and registers of the VM from the hypervisor and the host operating system. Because we have memory encryption, this protects against offline DRAM access. But AMD very specifically does not consider very sophisticated hardware tampering as part of the threat model. For example, active DRAM corruption is not something that they consider part of the threat model that they're trying to protect against. If this is part of your threat model, you have to protect against it in a different way. And Apple, with their private cloud compute, has done a really good job of considering the hardware aspects and hardware implications and how to protect against those sort of attacks. The last thing is that this technology also does not necessarily protect against architectural side channels. We still have to write constant time crypto code. Stuff like Spectre is still possibly a challenge. That being said, over time, some side channels have been pulled into the threat model that AMD tries to protect against. So stuff like indirect branch protector poisoning is something that a VM can choose to opt into protection for. And this last point is really important when you are considering your specific threat model, right? It's really important to understand exactly what generation of technology you're using, as well as what specific CPU your workload is deployed on. Because as time goes on, more and more of these protections have been built into and pulled into the threat model. Okay, so let's switch gears a little bit. Let's talk about confidential computing specifically in the context of the transparency ecosystem. So I went down this rabbit hole because I wanted to run a witness, but I did not want you to have to trust me, because at the end of the day, I'm just a random person on the internet. And so let's make that very clear, right? As part of our untrusted entities, the main one is actually the witness operator. And notice that the cloud provider is not actually part of this list. Although confidential computing is pitched as a way to isolate your guest from the host, we can also use it and get a little creative to instead shift around who we are trusting. And so to that end, as part of this, Google Cloud Platform is actually part of one of the trusted entities. And this is because I'm using more than just Compute Engine, I'm using some other services they provide. And we'll get into that in a little bit. Of course, AMD has to be part of our trusted entities because they provide the hardware, right? There's no getting around trusting them. As part of this, we're also trusting GitHub Actions to produce container images that are signed with cosign. And finally, we have to trust the application. The application, by definition, has to have access to perform operations with our keys and our data. And so if we can convince the application to sign the wrong thing or do something that we don't want it to do, then none of the other things really matter. In this case, I chose to use OmniWitness, although there are, of course, multiple witness implementations that we could have used instead. Okay, so let's look at how this witness is laid out in the cloud. So to start with, we have a virtual machine running in Compute Engine. And this virtual machine is running Google's confidential space operating system. This operating system is nothing more than Linux, just very much locked down. There are no configuration knobs. There's no SSH access. All the operating system does is it looks at the virtual machine's metadata, pulls a container image, and launches it. If your application is stateless, this is really all you need. But for our case, with witnesses, we do need some sort of state. We need access to a place to put signed checkpoints. We need a private key to sign these checkpoints with. To that end, we're using KMS, the key management service provided by GCP. And the KMS allows us to apply fine-grained IAM policies for restricting who can use the key. And this policy is what is going to let us actually restrict use of the signing key to just our witness. So the other thing this confidential space operating system does is at boot, it will first request this attestation from the CPU. I'll send this attestation over to IAM. And IAM will return, once it validates this, this attestation, it will return back a token with a bunch of attributes that we can use to craft that IAM policy. And we can apply a similar set of protections to the actual storage bucket. So let's look at this IAM policy. And this is where things really start to come together. One of the attributes that is provided in this token that IAM will give us is the actual reference of the container. And this reference is a SHA-256 hash. As mentioned previously, the SHA-256 hash is also signed by cosign and linkable to the source code used to generate that image. And so with this policy, we now have a way to link use of the signing key all the way back to the actual source code. And this is a really powerful thing to give someone, because now instead of trusting that I'm running a witness that will not sign the wrong things, you can now actually just go and look at the source code and know that there is an actual link all the way through. Now, finally, there needs to be some way for an outside observer to actually check that all this is configured correctly. And this is not super complicated. What we do is we pull audit data and a bunch of other data about the state of the project within a GitHub Actions workflow, and then publish this into a Git repository. This allows you to know that this data was not changed before it was published. And then an outside auditor or third party can come in and actually validate the state of the project and validate the configuration to make sure that this configuration matches what we expect and matches that entire chain of trust is actually enforced correctly. And this workflow runs every couple of hours to make sure that over time, right, that third party can verify that the project has not been, that the configuration of the project has not changed over time. So the code to this project is open source. You can find it on GitHub. I also have a test witness running in GCP based on this architecture. And you can find the audit logs for that witness also on GitHub. Yep, that's all I have. Happy to open up for some questions.
Hi, Tiziano from Google. Great talk. I really like the trick that you use to dump the policy. Would you say that that's, even if you are the owner of the project, there's no way for you to get around it, like deleting audit log records or anything like that? Obviously, you can change the IAM policy. Yeah. I assume you are assuming that it will show up in the records, but can you not go and delete those records at all?
Yeah, so the Google Cloud Platform ensures that, or provides this, Google Cloud Platform guarantees that the admin audit logs are read-only and kept around for, I think, 2 years. Okay, so cool. It's a guaranteed platform.
Thank you.
Thanks for your presentation. So more than a question, just like a tip, and maybe we could collaborate on this. So we're working to get Tamago running on enclaves. It already runs on Google Cloud Compute on its own. So I think an application for this is that you can just get rid of the OS layer there, right? So you are now going to need an OS and a container, so you can just run the Omni witness in the trusted enclave and just get even less dependencies on it. So maybe we should sync on that, because I think it would work great with this. But again, thanks for the presentation.
Yes, for sure. There's a couple of other projects that are like doing unikernel stuff, but I'm really excited to see Tamago in this space as well.
Hi, Ed. Thanks for this talk. It's great. My question is, how does the believer trust that the endpoint they're talking to when they're talking to the witness is actually the workload that's reflected by the configuration in the repo?
Yeah, that's a great question. So for witnesses, one nice property we have is that every checkpoint is signed by a private key. And we can get this private key out of band directly via KMS. And so the auditing workflow will actually also pull the public key directly from KMS and publish it out of band. And then you can use that to validate that you have a connection directly to what you think you're connected to.
Okay, thanks.
Any more questions? Okie doke. Well, let's say thank you to Edith again. I am apparently slowly losing my voice, so you'll have to bear with me. Okay, so that's the end of our first topic session. Whilst the guys get mic'd up for their talks before we start the website transparency session. There are a few things I should have told you this morning, but I was half asleep, so forgot. So I will remind you of them now. Today, just a little bit about today's schedule. We've got wonderful talks, wonderful sessions, just like yesterday. Similarly to yesterday, we will have a break after the website session. Be outside. There's food all the time. There will be food again, and then we will have lunch similarly in a similar place down to yesterday. There'll be an afternoon break, and then this evening we have for everyone at the conference, we've got a dinner booked at a restaurant that's just a 6-minute walk away. So that's already, this evening's activities are already sorted. Obviously, it's not mandatory, but we would love as many of you to come along as possible, continue the discussions, continue the collaboration. That would be really good. During the day today, later on today, we have breakout sessions again. A reminder as to how you sign up to one of those. I know Frederick was mentioning they're going to run a breakout session on the the Teletis HSM. It hasn't been written up there yet, but so if you have an idea for a breakout session, if you can go and write it on that whiteboard in that corner as soon as it comes to you. We'll do similarly to yesterday. There'll be a period of time before it where people go and put the dots, and then we spread you out. But just a reminder to have a think about breakout sessions. And then another thing to remind you about is tomorrow we have the unscheduled lightning talks session. We've had a few people sign up already. That's great. If you want to be involved in that, come and tell me or Al, who is still in red. Give a wave. There are some people here who weren't here yesterday, that's fine. Or Rasmus in the cap, and we will get you put on that list. The lightning talks for that we're talking like 2 to 5 minutes, like short, sweet, no slides, just come and chat for a bit, ideally on something vaguely transparency related. And then the final reminder, if there are any speakers here who have completely forgotten, if you can take a look at the schedule as to when you're speaking, and look up it and find the break that's before the chunk of talks that you're in. And during that break, come and talk to the production team and get your microphones. That would be really good just to keep the flow of everything. Okay, so with that, we will move on to the website Transparency Talks, and I will hand over to Michael and Dennis.
Thank you so much. So, my name is Michael Rosenberg. I work at Cloudflare, and today I'm going to present web application transparency along with my colleague Dennis Jackson from Mozilla. So, starting with motivation, I really want to run Signal on my browser. I really want to be able to go to chat.signal.org and specifically get JavaScript code from the server and do some encryption on my end, and then send some message to the server, and then have that message get sent down to the recipient. And one important property about Signal is that it has to be secure even in the face of a malicious server. If the server decides to act completely maliciously, my messages have to still be encrypted. Unfortunately, this setup makes that impossible. If the server is malicious, it can just serve me malicious JavaScript, and then whatever thing I do for encryption is up to the server. So for example, the server can just send me JavaScript code that exfiltrates all of my messages. Now, this is actually a general problem. It's not just for Signal, obviously. Thomas Tacek wrote about this in 2011, and this has been a problem on the internet since the beginning of the internet. It wasn't made for this. So there are plenty of things that you can't do in your web browser securely. You can't do confidential compute in your browser. You can't have a password manager in your browser. You can't vote in your browser. And you can't have a cryptocurrency wallet in your browser. So to get intuition for why, for how to fix this, we'll look at an ecosystem where this is not a problem. So if I have the iOS app for Signal, I don't have the same issue. Why is that? So I get my iOS app from the App Store, which is a third-party distributor. This is the party that's trusted to give out copies of the binary to individual users. This gives us 3 properties very roughly. Integrity, which is it is difficult to maul the apps once they are sent by the App Store. Consistency, which is to say that every user gets the same app, roughly. And transparency, which is that app versions that are published by the App Store are visible at the very least to the developer themselves. And some app stores do this to an extent and some don't, but this is roughly a property that exists. Unfortunately, app stores have downsides. Mainly that they're extremely centralizing. App stores wield an immense amount of power, arguably more power than any single party should have. So we would like to get some of these features for the open web without centralizing in a single app store. And to be more specific, we have some desiderata for any kind of scheme that we'd like to make. So first off, we want this to be strictly opt-in. We don't want anyone to suffer from any kind of deployment if they don't want to participate. Security should be free for end users. So a browser should not have to pay in latency cost if they want to use this feature. So there should be no extra network round trips. Similarly, browsers, in the same spirit of being free, at least performance-wise, we don't want users, end users, so browsers, to spend any extra storage space on a per-site basis. We also don't want users to have to exchange transparency for privacy, so we don't want any extra fingerprinting vectors to be introduced. In addition, we want this to be an open ecosystem. We don't want people to have to pay for the core service. We want an easy on-ramp, an easy off-ramp, and we want this to be as exposed as possible to the browser APIs so that people can build plugins and build on top of transparency and benefit from all of these security guarantees. So in this talk, we will talk about a constellation of specifications known as Web Application Integrity, Consistency, and Transparency, or WACT. This is very early work, and it's work between browser vendors, cloud service providers, and encrypted communication providers. We'll split this talk into 4 parts. So first we'll talk about the web application itself, defining what we mean by integrity. Then we'll talk about the transparency service. We'll talk about how this looks on the client. And finally, protocol extensions. So first, what do we mean by web application? So the end goal, spoiler, is to put things in a log. So for an Android app, this is easy. You just have APK files and you stick them in a transparency log. You can't do this with web applications. Web applications are much more diffuse than a single APK file, right? It is a set of pages, and each page might have different assets that it loads. And these assets can be loaded either from external servers or locally on the server. And in addition, pages can link to each other, and each of which might have their own set of assets. So this is very far from a single APK file. So our first step would be to constrain and fully define the entire web application in one thing. So we can do this in 2 steps. First, we can constrain each page alone using sub-resource integrity, which is an existing web standard, which basically says every time you load an asset, you specify the hash of that asset. And when you receive that asset, you compute the hash, and if it doesn't match, you reject, meaning different things in different scenarios. And so this essentially constrains each individual page to be well-defined with respect to the assets that it loads. The pages can't do anything anymore outside of exactly what the code says. However, pages still link to each other, and you can't have an integrity manifest on a hyperlink. So there's still some malleability here. So the second thing you could do is have an integrity manifest, which is defined in one of the WACT specs. And this is essentially a file that contains the hashes of, for example, all the HTML files under a path for a single site. And this is the final step. This narrowly constrains all of the pages together into a single thing. And so this is this single manifest is going to be the thing that defines what a web application is. So all of the operations that we do for transparency are going to be operating over this manifest or a hash thereof. So now we can talk about what the transparency service does. So the transparency service is a service that manages the main data structure of our transparency scheme, which, surprise, is a tree. Specifically, it is a prefix tree, aka a trie, which is a tree whose leaves are indexed by strings and are sorted by prefix. Each leaf has a hash chain of the manifests that have historically belonged to the website, and this hash chain is an append-only data structure. Some people use Merkle trees in this scenario, but hash chain also happens to work. And finally, there's a witness, which we won't describe in too much detail, but basically the witness does the thing you'd expect. It ingests a stream of events from this transparency service and updates its own copy of the prefix tree and reconstructs the root hash. And if it agrees on the root hash, it'll cosign the head. Finally, since manifests grow quadratically with time, assuming a constant rate in the number of sites that are enrolled in transparency, we can't store manifests forever. We have to have some sort of eviction policy for these things. So just imagine some cutoff on the transparency service. So we obviously need a monitoring story. So what does this look like? It happens to be very efficient. So if a user wants to monitor their own site that they've enrolled in transparency, they simply ask for a site, and they get the inclusion proof of their site in the prefix tree. And all they have to do is check two things. Check that the manifest hash is unchanged from the last time they requested this proof, and also check that the time created of this leaf is unchanged, which is to say it hasn't been unenrolled and re-enrolled, because that would have given it a new timestamp. This is significantly more efficient than the process of tailing a log. I'll describe this quickly. So in the certificate transparency case, as we know, tailing a log can be quite expensive for bandwidth. So if you only have a gigabit per second of bandwidth, you can support about a few thousand monitors. So in particular, this means that you can't self-monitor not everybody can self-monitor their CT, their certificates. They have to rely on a monitoring service. On the other hand, if you have a log with structure, you can query the log and get back the latest value and know for a fact that nothing has changed since the last time, so you don't have to do the same tailing process. Borrowing an analogy from Brendan McMillan, this is the difference between reading through an entire stack of papers versus using a filing cabinet. So with the same amount of bandwidth, this can support about 2 billion monitors, which means that people can actually self-monitor with this. So finally, one of the main properties that we need to ensure for a transparency service is that it is not too centralized. So we want to avoid this any kind of lock-in property that would happen. And so currently, if we have a single transparency service, this means we have a single point of trust and a single point of failure, which is a problem. So a natural solution is to permit many transparency services. And we have to be careful here, because if we permit 1 million transparency services, then we have an auditability problem. Yes, maybe we have transparency, but there's no way to even check what is happening anymore, because if there's 1 million users and 1 million different manifests, then how can anyone make any guarantees about what's happening on the website? So the property that we kind of want is consistency, which is everybody gets the same version of the site. Now, we can't actually achieve that because consistency is a very strong property, and we can't guarantee that everybody gets exactly the same version, but we can weaken it a bit and say roughly everybody gets the same version. So how do we weaken that specifically? Well, we allow transparency services to serve different copies of the manifest. So if depending on the transparency service, you might get a different copy of the manifest, and also there might be multiple manifests that are valid at a given time. So you can get, a few manifests possibly into the past that are still valid. So instead of 1 million, you have a handful of manifests that could be in play at any given time, and this is far more reasonable. So that was the server side, but to talk about the client side, I'll give it to Dennis.
Thank you, Michael. Thanks, Michael. So, the client-side perspective on this is challenging. So obviously, some websites are going to want this stronger security model, but not all of them. So the first question is, how do clients know, how do browsers know which websites have been enrolled in transparency and that want this stronger security property? If they've been enrolled, how do they know that the website is presenting a transparent set of an application manifest? And when things go wrong, how does the client respond? What happens next? What's the recovery story for both websites and for users? So telling clients about enrollment, The sort of obvious solution is, just have the browsers, they're connected to the internet, have them talk to the transparency service and ask, is this website using this strong transparency property? And this has real issues. You typically can't assume that browsers can talk to a third party. You can really only assume they're talking to the website they're actually connected to. It would be horrible for privacy because you'd be revealing to that transparency service which website you were interacting with, and you'd be adding latency in the form of round trips. So this is a bit of a non-starter. But what we can do is have sites tell users that they're enrolled in a kind of trust on first use model. So think HSTS, if you're familiar with that. The site is just going to tell the website, so the site is going to tell the user, I'm enrolled in transparency, hold on to this, remember this. And this works, but we have users that run in private browsing mode and that might want to do confidential things on a site in private browsing mode. And in private browsing mode, we can't store state. We can't store state about the fact that a site's been enrolled. And worse, sites know when a user's in private browsing mode. So this would be a particularly convenient way to attack users that are definitively not doing transparency. So what we can do instead is we can give all the browsers that we distribute a big list of all the sites that are using transparency. And this is similar to HSTS preload. And the problem with this is really list management. Like we, as the browser, have to basically manage this huge list of who's enrolled and who wants to be enrolled and who wants to be unenrolled. It's time consuming, it's difficult, and we don't love it. But actually, we don't know of a better way. So if already you think you see a better way to achieve this kind of downgrade resilience, we would certainly love to hear about it. So once the browser knows that it has to enforce transparency for a particular site, the story is then relatively straightforward. The site's going to have to present this manifest that Michael described, an inclusion proof, proving that that manifest is in a transparency service, and then a bunch of signatures from the transparency service, from some witnesses, to show that it's been logged correctly and that it's been supported. But each one of these steps is a different place where something could go wrong. The manifest might not be passable, the inclusion proof might be wrong, the signatures might not validate, or they might be from witnesses or a transparency service that the client simply doesn't trust. And what are we going to do when things go wrong? Well, we're going to show them an error page. And if you've used a web browser, you've obviously been infuriated at some point when a site you've needed to access simply hasn't worked. And this is a real problem because obviously the story we'd like to tell people when they see an error page is very, very bad things are happening. Stop what you're doing. We're doing a great job protecting you here. But in practice, something's gone wrong. There's been a bug. There's been a misconfiguration. An intern's been let loose on prod. And, really this error page, from the user's perspective, these two situations are indistinguishable. And certainly the second scenario just seems much more likely. So if we tell users we're adding more error pages to the browser, they're not going to be happy. And I think website operators are also going to be pretty unhappy with that outcome as well, because it's risky to enroll your site in a new security service that might bring your site down for your users. So what can we do here? We've got this kind of enrollment signal. We've got this list that we have to manage that we may not be able to manage especially dynamically. What we're going to do when it all goes wrong. So we've got some faulty proof being presented. We've got an unhappy browser that won't load that site. We're going to give people an escape hatch. We're going to give specifically website operators a way to bail out of this system. And that looks like a special kind of tombstone value, a sentinel value, that is logged transparently. So that when clients are shown a tombstone value that traces up to a valid log, they just treat that as unenrollment. They no longer enforce transparency for that site. It's over, it's done. And from that client's perspective, carrying on, they don't benefit from the security of this system. But the fact that a website has issued this unenrollment signal is itself transparent. So monitors and third parties can see that a site has chosen, something's broken, and they've decided to unenroll. And this really sort of brings us onto the wider ecosystem, which is that client enforcement is important for any transparent system, but it's not the end of the story. So if, for example, you had a service, say Signal was enrolled in this, and that the Signal issued a tombstone value and an enrollment every week, the system would have no value. And this is like primarily a social problem that can actually only be addressed through policy and culture. Like similar problems are very much like if you've got a given list of manifests for a given website, those manifests correspond to good code or bad code, not addressed within the scope of this system. Now, there are things that you can do to solve that, the techniques from binary transparency, like reproducible builds, scanning for malware, etc., etc. But they're very much going to be on the basis of an individual operator. So we're going to provide a primitive here. It's going to provide a security system, but what people make of it is actually going to be more down to the website and the operator and a cultural expectation as it is about anything else. And I think this is true of most transparency systems. So we sort of talked through the client side there, and now we're going to look at the extensions very quickly. So we could certainly imagine that this threat model might not be right for you. In particular, we're going to sort of focus on making sure that this remains available, but you might want stronger security. You might want cooldowns on specific changes. You might want stronger code signing properties. And we see a way to extend this through the existing kind of browser extensions platform, where they can mediate this and impose stronger requirements, for example, if they'd like to. Similarly, applications might not be the only thing that you want transparency for. So there's a whole family of privacy-enhancing technologies making their way onto the web. So some examples are the things from Privacy Pass, like private access tokens and private state tokens, or IP protection systems like VPNs, private relay, mask. These technologies rely on a shared configuration file, and users only get privacy if they all have the same file, and transparency can be an important way to provide that. You also, might be updating your clients remotely with a log list, and maybe you'd like some transparency for your system, your changes to your transparency enforcement. This work is still at a very early stage, as Michael stressed at the beginning. There is a general explainer of the overall system that's available on GitHub that sort of talks about these different components and how they fit together. And more specifically, there's a transparency draft, which is sort of actively being developed. There's no running code yet. There's just a bunch of prototypes. And we would really love the community's feedback, especially on this aspect. So issues, PRs, suggestions, doom, optimism, it's all welcome. Thank you.
You mentioned that one of the problems you have is figuring how the website can opt in to this transparency feature. Have you considered that, well, at some point, somebody will most likely resolve a domain name to an IP address so they can connect? And maybe you can also provide that kind of hints on the DNS so they are secured using DNSSEC.
Yeah, that's a really interesting idea. The main concern with DNSSEC is that its deployment is fairly uneven. So a substantial fraction of sites don't have access to it because of particular issues with their higher level domain registers. Another issue is that clients have typically been reluctant to enforce DNSSEC because misconfiguration breaks sites. So in the situation where you receive a DNS record and it doesn't verify, clients typically tend to trust it anyway. So I think it's the kind of thing that we could use as an adjunct, but I don't know that it's the kind of thing that we could rely on exclusively. But yeah, it's an interesting suggestion. Thank you.
Hi, thank you for the talk. In the beginning, in the slides where he had showed like statically generated pages like index or about us or anything like that, that's typical of basic static pages. What are the thoughts around dynamically generated pages of various websites outside of just the fact that assets on pages changes every day, if not several times a day, depending on the development cycle where you are at. So I'm just kind of wondering what was the thinking around dynamically generated pages and how to check the integrity on that.
Yeah. I mean, this is a tough thing that we don't have an answer for. If a page is dynamically generated, then it's really hard to make any claim about what the hash is going to look like. Theoretically, you could issue a manifest every time it changes, but often dynamic pages change also based on every user. So it's not so much for that. This is definitely an interesting problem that we see for maybe future versions, but for now, it's something like you know, I have a progressive web app that has a really small set of HTML, CSS, and JavaScript stuff. Like I'm self-hosting CryptPad, for example, right? Like how do I get any amount of transparency or code signing on something like that? So yeah, the scope is more narrow than that, and that's an unsolved problem.
I would say that, you know, some web developers are willing to go the extra mile to try and make that work within their system. So Meta, for example, have a code verify extension, which effectively tries to do a similar thing to what's being described here for integrity. And obviously at the scale of Facebook.com or Messenger, that's a you know, incredibly complex operation. But they've been willing to invest the time and energy to make it work. So I think there's reason for optimism.
Any more questions? We have plenty of time. We are running ahead.
Hi, thank you. Who runs the logs in this system?
It's effectively, if you like, a root program model, you know, in the sense that anybody can come up. We envision that anybody can come along and say, hey, I'm willing to stand up a transparency service, and with a certain amount of impetus, we can, you know, check that they're doing that correctly and then trust them to do it. In the beginning, seeding these things is always hard. When you sort of go back to the early days of the web PKI, there were certainly some interesting deployment models for how CAs operated. We could certainly imagine bootstrapping this to make it work, but I think we'd have no interest in running it super long term. We would ideally want to hand this over to interested parties.
Thanks very much for the talk. I'm curious to hear more about the eviction policy that you mentioned for the manifests. Do you have thoughts on, is this something that's time-bound or based on the amount of manifests? I guess I'm curious if there's some opportunity where someone could maliciously generate enough manifests for a site that you end up evicting something and hiding some content from a verifier.
Yeah, that's a very good point. We don't have any specific eviction policy in mind right now. Just a note that one has to exist. Otherwise, you just get infinite storage. Actually, I encourage you to make that as an issue on the GitHub.
If you're using an extension to monitor more of the transparency, it seems like you're putting a lot of trust in that extension. And like, is Mozilla planning to have like transparency for extensions? Is maybe the next question.
Yeah, I think transparency for extensions is a really interesting area.
Amazing. Well, let's say thank you to Dennis and Michael again. And I would like to invite Giulio to the stage for our next talk.
Hi everybody, I'm Giulio. I'm a researcher of the Freedom of the Press Foundation, and we have been researching and working on integrity and transparency for web applications since 2022, with a particular focus on difficult threat models, including Tor browser. We could name the project WebCat, just because we like cute names. So the browser JavaScript crypto problem is pretty known by now. The previous talk did a great job at explaining it. In a few sentences, the problem is that every time you visit any kind of web application that does client-side cryptography, whether that's end-to-end encryption, attestation, even verifying downloads, you are trusting not only the developers, but any front-end service or middle boxes that is in between. And that adds a lot of potential attack surface in the chain. And second, the other problem that's particularly keen to us is that most browser exploits rely on JavaScript for either exploiting the JavaScript engine or for building payloads. And that's not only about remote code execution, but also about de-anonymization attacks to Tor browsers or fingerprinting or stuff like that. Now, if we imagine desktop application and how to diff them from web application, especially for distributed and federated services like self-hosted stuff, there's clear differences that we can highlight here. Now, if we think, for instance, of a Matrix client, generally in the mobile and desktop world, you install the app once, then you configure it for your instance, or you use your account, and you contact a third-party service. For web application, generally, when you self-host something, like Jitsi, that even though that's mostly a client-side web application that connects to a backend service, operators are kind of incentivized to host their own version, also because you don't want to visit a third-party website and host even and put trust in even one more hop in the loop. Now, what we would like to go from here is to kind of tighten the gap between web application and desktop applications in a way where users can actually trust developers directly and remove as much trust as in between as possible. The system that we've been working on has two main data structures, a policy and a release or a manifest. And they have different functions and different life cycles that influence how we choose to log and treat them. A policy is a description of signing keys, logs, and witnesses, and some conditions that define when a policy has to be considered satisfied for a certain artifact. A release is a description of a web application. That's actually a pretty complex thing to do because a web application has a lot of moving pieces, and you need to check all these pieces. And these include matching hashes to a path, but also the content security policy is a big piece of the trust model and the security model for a web application, and then some additional metadata that actually allows you to track what this manifest is and how to verify it against a policy. These two data structures have very different life cycles, because when you think of a policy, the policy is mostly long-lived. It can change across the years because you maybe need to rotate keys, you maybe need to refresh your witness list, but mostly it stays static, while what you actually want to do is do new releases of your software according to that policy. So in a few years, that might change a few times, while releases can actually happen even daily if you're publishing snapshots. And these two timelines kind of influence the design a lot. So the idea is that you bind a policy to a website in a list that has to be transparent and secure and have a bunch of properties. And every time you do that, the policy is hashed and bound to a domain, and this list is shipped to the browser. The model implies that there's different development and hosting models. If you think of WhatsApp Web, WhatsApp develops and serves their own service, and there is no purpose for third-party hosting because that's just the centralization that they want. If you're thinking for self-hosted services like CryptPad, where the idea is that they develop it, they have a flagship instance, but then everybody hosts their own, then the model is slightly different because you want to actually trust the original policy and the original developer and not the hoster. And so what you will do in this case is that CryptPad will publish a policy, bind it to their domain, and then all the other instances could reference that policy. And that information could actually be passed down to the user. Like, all the verification has to happen transparently, but if one user wants to be extra safe and check, they can just get this information and say this website has been verified against CryptPad.org. Now, TLS and WebCat, this comparison is done mostly to give an understanding of the conditions. They actually have not a lot in common, but it's mostly to understand the threat model here. So in TLS, you don't have specific consistency, even if it's not the correct term. You can have multiple certificates valid at the same time for the same website. In WebCat, there is one global policy for a domain, and so you don't need reconciliation when monitoring, because if that changes, that affects everybody, and there's no different versions of that. Similarly, in TLS, for good reasons, you want your certificate immediately, so you solve your ACME challenge and you get your signed certificate. For WebCat, we don't only want detection, but we want prevention. And so what we want to do here is that we don't want sudden policy changes, but we want them to be delayed over time, so that when you actually ask for a policy change, the request is transparency logged, but it's not applied immediately, and there is a waiting window where if you actually detect an anomaly, you can revert the change and stop that from happening. If you satisfy the condition for the continuous proof of ownership, then that is actually logged again, and the change is confirmed. In Tor browsers, there's particularly threat model that make it so There's a few conditions that are more difficult than in a classic context. We don't want any censorship risk, so we want people to be able to bring their own log, and so that they can specify that in the policy, so there is a good distributed ecosystem of different parties. And people could host their own, and it's not super expensive in this context because you might actually logging a few manifests. Similarly, the place where we store and verify the policy has to be distributed and consensus-based, so there's no single party that can decide who's in and who's out. And lastly, to close back the circle about the exploitation, Tor browser currently has a security slider where you can either allow JavaScript, allow a subset of JavaScript function, or disable JavaScript globally. If we actually have the list and the policy hashes of known applications, we could imagine an extra feature in the slider where you could choose to enable an allow list of known web applications that actually can be run on a subset of unknown domains, because we could be actually just allowing the policies and not the specific host, and allow those policies on any host that reference the original one. So you could have a CryptPad on any hidden service authorized. If you want to read more about this, the GitHub repository is the place where we're working. As mentioned, we've been working a lot across over the last 3 years. We've ported some web application to this system. The document on ePrint is a bit outdated, but like the threat model and the requirements are pretty clear. And our development blog is at secure.org. We hope to have a breakout session about web transparency. So if you're interested, please join it. I'm sure we can have a very productive discussion. Yep.
Questions? Yes. If I wait long enough, someone will put their hand up.
Hey, so thanks, a great talk. I was wondering about the policy. Yeah, how do you envision the policy will get to those who need to have it?
So the association, like the key value list between the hash and the policy, has to be shipped to the browser beforehand, like the HSTS mentioned that was done before. The policy is served by the same website so that you don't have to do extra round trips. And of course, if you are hosting CryptPad and you're referencing the original CryptPad policy, you have to serve the same policy, and then the local lookup will check that in your local list that actually match the CryptPad one. So everything is either served by the same website or it's looked up locally. For this, there has to be an enrollment system. When we fetch the policies, we lock them, and we enforce the waiting period, and that is currently a consensus-based distributed system, so that there's multiple nodes.
All right, over here. How much have you implemented so far in terms of like prototyping, and have you also tried porting some applications to actually run with this? Because yeah, it seems kind of hard in as question for the earlier talk about the dynamic websites and things like this. So how much prototyping have actually been done, and what have you learned from that, if you've done any? Yeah. Thank you. So we actually implemented the full thing at the beginning of this year as a Firefox extension. The old version used Sigstore and is a bit more locked in, but as much as the enforcement and other parts, it's all there. It's in the GitHub repo. It has been pretty difficult, so we worked on porting Bitwarden, Jitsi, CryptPad, and Global Leaks as applications. And it's not so simple because like one of the goals of this system is to be compatible with open source software, and we don't actually want to ask open source software developers to fully rewrite their software to be compatible with this system. And so you have to find a good balance of enforcing the properties you want, but also not requiring rewrites. And that's a bit difficult because the web has a lot of complex technology in this front. There's workers, they use iframes for sandboxing, like how do you recursively look at iframes to ensure that like this property is assured. And that's also why we insist that like the content security policy is kind of a key piece in this, because it's used for sandboxing. It's used to isolate workers from the main context, like there's many parts in that. So we worked a lot to see what are the actually real world issues, and there's many.
Okay, another question. Could you explain a bit more what it means to bring your own logs? So every website could have their own log if they wanted. Like, for example, Alcatra have been working a bunch of serverless log where you kind of run your own log. Is that something that would fit into this, or did I catch that wrong?
Yeah, so currently we are using Sixam because it's like the most open available thing, but also Sixam doesn't allow us to have, at the moment, freshness proof, like it could be built, but it's not part of our prototype. But the idea is that surely there could be some big logs, like there could be big providers that provide the log either as a service or either as a community benefit. But at the same time, if, for instance, I want to do a log that's for open source developers because we subscribe to the same values and we want a thing that's self-hosted and part of the community, then you can specify that in your policy and you can use that one. Since the policy allows for multiple logs, you can also have backups and you can like have your primary ones and they say if Mike goes offline, this is a backup option that I could be using. But the idea is to have a very open ecosystem as much as we can. Also because Tor has had a lot of concerns about NER coding because it becomes a potential target for censorship. Thank you.
Okay, let's thank Julia again.
Thank you.
So now we have a break. We are running a little bit ahead of time, so the break will be a little bit longer than it was planned to be. We will be back in here at 11:20 to start again. See you then. Okay, our next session, package management. So one second, blah, 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 blah. Okay. You're good? Yes. Hello, everyone. Welcome back. I hope you had a wonderful break. We're going to get started on our next session now. We have 3 very exciting talks for you before lunch, all on package management. So with that, I will hand over to Michiel, who is going to talk to us about Go module notifications.
Thank you. All right, so my name is Michiel Kien. I'm from the Netherlands, live in Amsterdam. I work as a freelance software developer, but I actually do quite a bit of open source projects, mostly in Go, because I love programming in Go. So Go for Watch is one of these projects, but actually most of my time has been spent on a mail server called Mox, so for sending email. It also does IMAP, ISMTP, all that stuff. And that's the reason why Go for Watch exists. I wanted to send out some emails. So, log transparency is a great excuse to do that. So what is Go for Watch? It's a service. It's an open source application. I run it as a service. It's a free public service where you can create an account. You can sign up for some Go modules that you want to monitor. And then you'll get notifications when new modules are being published, the new versions are being published. You can also nowadays get webhook calls due to popular requests. So if you don't know exactly what Go modules are, if you're not too familiar with the Go ecosystem, think of it as a package. It's a unit of versioned pieces of source code. And this is an example of my mail server. So this is a Go module path, this example, which is essentially like a location or a bit like a URL. It has a hostname part and a path part, and there's a Git repository behind there where you can fetch the source code. The Git tags are just versions. They're semantically versioned in the Go ecosystem. So you can register for notifications for this module, for example. And you're wondering, where's Go for Watch getting this stuff from? And of course, there's a transparency log involved. It's the GoSum database. You've heard about this before. Essentially, all the Go modules in the Go ecosystem are in this transparency log. It's run by the Go team. It lives at sum.golang.org. So next question is maybe, how do all these modules get into the GoSum database? And as Filippo mentioned yesterday, when this GoSum database was introduced in the Go ecosystem, it was just turned on and all the developers were using it. And that's because it's integrated in the Go tools. So if you use Go Get to fetch some dependencies, they go first through the Go module proxy, which is a cache of all these modules, all the source code. Then your Go tool will check that the hash of that source code is in the GoSum database. Now, as a developer, you're contributing to getting all the entries into that GoSum database, because if you edit your source code, you add a new dependency, which is like you add one of those import paths, one of those Go module paths, and you run Go Get, then your Go tool will go to the Go module proxy, ask for the latest version, and the Go module proxy will go off to the origin version control system, GitHub, for example, and see if there's any new tags, and if so, download the latest source code and get that entry added to the GoSum database. So all the developers all the time are sort of helping discover all these modules. And likewise, if you compile an application, so a library with an application, in Go, those are just also Go modules. You're often instructed to install the latest version. So you'll go off, get the latest version, and ensure the latest version is visible in this GoSum database. Now, you may be wondering, what use is monitoring source code? And I guess we can figure out why certificates can be monitored, but is source code monitoring that important? Well, here's some inspiration of what you can do with that. You can check your dependencies of your application, see if they're updated, and if you want to update through them. You can do this other ways as well, but with monitoring the transparency log, you can do this for all, wherever the source code is stored. Likewise, if you use applications written in Go, you can use this to decide whether you want to upgrade, to find new versions. You can also use this to see what your company is up to or your friends are up to. So if you work in a big organization, you may not know exactly what everyone's doing. I can just see if any new releases are happening. And of course, you can detect unauthorized publications of source code. So if you see a new version or a new module that under your domain or your account, and you don't recognize it, you should check out, see what's going on. And also, you can do all kinds of custom automations with this. Create pull requests for updating libraries, or run a new test suite as soon as a new Go toolchain is published. So not only does the Go Sum database have all the Go modules, the source code in the ecosystem, also the new Go toolchains are added to the Go Sum database. So you can discover new Go toolchains. This is what I'm doing for verifying that my source code still works right after a new toolchain is published. Then I'd like to do a demo. So let's see if this all works today. We go to the Go for Watch website, which has a bunch of text explanation that I've just mostly given you. So here you can see that this is a real-time thing. Just 3 minutes ago, lots of entries were added. And just showing this, that I have this on the website just to see it's live. You can maybe, if you are bored, click on all those links and see what this source code is about. You can see that many of the source code nowadays is hosted on GitHub, not a surprise. Some more text below, but let's create an account. The best way to do that is to send an email to Go4Watch, because that way we automatically verify that you own the address. And it's also for spam reputation issues. So I'll just open this. This is a pre-composed message that it's suggesting, so I'll send that. And if all is well, we should be getting a reply back real soon. Yes, there we go. That's a bit much. Now we have a new sign up. So we click the verification link and add a password. So we're logged in now. So now I have an account on this Go4Watch service, and it's very bare bones. I agree. I'm not very good at UIs. We add a subscription. So we say I just want everything under my name. I want to monitor that. So including submodules, anything like any actual repository. I was going to skip this one. We want pre-releases like beta tags. I don't want notifications about just any commit, like these pseudo commits are just essentially timestamped with and git commits when they're not tagged. No comment. And I want an email when something, a new version is published or a new module is published. There's also options for adding webhooks. I'll skip that for now. You can disable your notifications for a moment. There's something about the health of your address. If you want to send to you and you're not accepting email, you can find out. I mean, you won't hear about it, but you can find out here what's going on. By default, I only send like one message a day, not to give you notification fatigue. But let's do it like instantaneous, and then there's history about what has been sent. All right. So now we have an account. Let's see. I've got here, if all is well. Got a bunch of commands ready to go. So I've got this little example Go module, an application. I've got it installed locally. It just says hi all. We can see inside the binary that this is version 001, and this is the Go module path. Let me again find. So now I've got a div prepared. So I'm going to say hi. Now let's see if this commits that div, tags it and pushes it to GitHub. Hopefully that works. Yeah, that seems to work. Let's find out, get my command. So now it should be available at GitHub. So it's discoverable, but it's not known yet. But if I now install this latest thing, I will go through the Go module proxy, which goes to GitHub. If all is well, that was really quick. That was not. That was too quick. Let me see what this is. Can I do it again? I'll just have to explicitly ask for it. So the Go module proxy doesn't do this every time you request it. Sometimes it just gives you a cached response. So by explicitly now mentioning the version, it fetched it, and the Go module proxy added it to the Go Sum database. And we should be running this new version. Yes, and you can see that this is indeed the new version. Now we should be getting a notification, but we don't have it yet. And that's because Some database doesn't have a real-time feed where you can get real-time entries. There's an endpoint to get the latest signed tree head, but it only updates once every 5 minutes. But there's a way around that. There's this special mechanism where you can find the latest signed tree head. Sometimes, of course, you need that. And that should, if all is well, give us a notification. Oh, dang, demos. Right, well, I was prepared for this. You get an email like this. I'll have to figure out later on what went wrong here. But you get an email like this. It says there's the module. It's a link straight to the GitHub page now. There's a helpful link to the Go documentation. There's a link, because GoForwatch recognizes this is a GitHub URL, it will compose a link that goes straight to the release page. So you can quickly see what changed. So this is just some updates to some dependencies. And you can also go straight to the diff at GitHub. Again, we can make that link. So this makes it easy to review what's going on. Let me go back to the presentation. Yeah, I'm very unhappy that notification didn't come through. I don't know what's going on. Some technical things about how this works. It's not very complicated, of course. GoForwatch is just a loop fetching the latest signed tree head. That's the URL where you get it. Then all the new records are fetched and verified, matched against any subscriptions that are in the database for any accounts. We queue notifications, and then there's a Go routine that sends, that handles the queue, sends email messages and webhooks. All the data is stored in a simple database thingy. So it's called a Bolt database, and that is an LMDB database written in Go. So LMDB is Lightning Memory Map database, very simple, one file transactional key value store. Most of the complications here are about sending email, doing email deliveries and handling feedback if something's not deliverable. We don't want to be spamming people. That's not good for the reputation when you send email. So you have to make sure you stop sending when people stop accepting your email. And one of the reasons, or the main reason why I wanted to work on GoForwatch as well, is I wanted to make this easier for Go developers or any developer to send email in an automated way, doing this transactional email stuff. And everyone's doing that with custom web APIs, and I also needed to design one. So this was like my use case to get some experience with sending that. So that's most of the technical stuff, but there's one more thing that's in GoForwatch, and that is, one more thing. First is that this is running on a GoForwatch.org is running on a very small virtual machine because it's not terribly complicated. But the additional thing there is that GoForwatch also has a DNS server, and that's maybe a bit unexpected. But you can look up the latest version of a module through DNS. So if you have this module path, you can do a request for a text record. So I've color-coded the name thingy because it needs a little bit of explanation of how that works. But you can see that you're getting the latest version number at the timestamp when this version was encountered in the transparency log. So this first, so on the right, the green part is the DNS delegation. Then there's a sort of a V0 is the DNS versioning, of API versioning. Then there's github.com as like the host name of the GitHub module, or the Go module. And then there's an underscore to separate the hostname part from the path part of the Go module name. And then there's the path part, but then split at the slash, reversed, joined on the dot, with special characters in DNS, like the dash, replaced, escaped with an underscore in the hexadecimal name. So that's, I have a bad name for an example, but so that works. You can use this to look up the latest Go toolchain. You can get like the currently latest supported version, but also the one from the previous release cycle. And now, in case you care about this, it's all DNSSEC signed, so you can trust it. And I created this because I wanted to very cheaply, with low overhead, check for updates, like an application to check for whether an update to itself or the Go toolchain is available. And the DNS requests are very small requests. They're cacheable responses. And this gives you a bit of privacy if you're doing all this testing, because you're probably behind a network DNS resolver, like a recursive resolver. So many machines are probably behind this. So it's like a nice combination of properties, I think. then I have to really hurry up. Some future things that may be implemented at some point, depending on if people really want it. Not all these ideas are by myself. Rasmus has had some ideas, and Filippo. Integrate with some more services, like webhooks are nice, but then many people may want Slack notifications, so we can just make that easier. We can help a bit better with tracking dependencies of all the dependencies of an application. So it's already relatively easy to import the current dependencies of an application in one go. But if you update your application, add more dependencies, you have to do that manually. But I think we can help you track that more easily. When I started GoVWatch, I think it was about 1.5 or 2 years ago. I didn't import all the history, but I probably want to do that. Silent monitoring mode, you know who suggested this. So you only get notifications about the stuff that you didn't expect, so you have to allow list what you did really publish yourself. So we need a mechanism for that. You could start detecting typo squatting of your name, domain name, package name. If something is released that's very similar, it could be suspicious. And you could also detect a domain or account takeover. So expired domains re-registered and new versions of a module published can be suspicious. So you may want to flag that and make you look at it. Okay, so that's that. Please give GoVWatch a try, make an account. It's free. The source code is all available. If you want to run it yourself, it shouldn't be too hard. I think a good way to do that is with sending the emails with mocks. And send me an email. I like email, obviously. And then there is some more things that I built with this afterwards. I promised it in a talk title, but there's a lightning talk tomorrow about more of this. So stay tuned. It has something to do with reproducible builds and transparency logs and doing automated updates with these components. So thank you for your attention.
Questions?
How many users does GoVWatch have, and how has that been growing over time?
Oh, I should have checked that. Yeah, for me to check it, I have to export a database, and because I don't have an admin page where I can see this. So I can tell you that operating this is very hands-off. I don't have to look into it a lot, so I'll have to look it up later on and tell you. But I don't think that there's a huge amount of Go developers there that are using it yet. But maybe there's some candidates here.
I have a question also. You mentioned that one thing we can detect with this is unauthorized releases, right?
Yeah.
How often have you seen that happening?
0 times. So that's a good thing, for me at least. But I know, for example, I guess when that happens, someone somehow got a git tag, some source code and a git tag, either in your repository or somehow convince the Go module proxy to fetch that. I don't think that's of course not an easy thing to do, but I can imagine that if your credentials get leaked, your GitHub credentials, for example, and someone else publishes that, then they could publish a new version. I think we've seen supply chain attacks where this is done. I've not seen it in the Go modules, but maybe it has happened, but people weren't monitoring their Go modules. They didn't notice.
Can you check if the notification email arrived now?
Oh, yeah, okay. That's a good one. No, still not. I don't know what's happening here. Did I make a typo here? No. This is indeed my... No, I'm going to investigate that right after.
Oh, okay. Do you consider having a verifiable index?
No, I'm very interested in that work, but currently I'm just tracking the whole thing and I guess streaming all the updates. And I think you probably need that if you want to do this for multiple accounts. It makes some sense maybe to ingest everything.
Okay, well, let's thank Michael again. And I'll invite Hayden to the stage. Where is he? Oh, yeah.
Alrighty. Well, hello everyone. Today we're going to be talking about software supply chain security and some of the work that we've been doing with package registries and making them more transparent. So if we haven't met, my name is Hayden Blausvern. I'm a tech lead and manager at Google on the open source security team, where I work on software supply chain security and simplifying code signing within open source. It wouldn't be a presentation here if I didn't mention the owl meme. And the reason we talk about this meme, right, is that we care a lot about the end-to-end story here. It's not just recording proofs and verifying them. It's thinking about the full end-to-end story. How does a verifier in this ecosystem ultimately verify the content that goes into the log? And when we talk about package registries, there's a lot of metadata that we're going to be verifying. There's attestations and provenance for how something was built. And as we're going to talk about in a moment, there's a lot of logs that we might be able to add to this ecosystem. There's a lot of places for transparency throughout the software development lifecycle. And so for that, I propose an extension to this meme. If this doesn't make sense to you, I learned recently that a group of owls is called a parliament. What I mean by this is that there's a lot of opportunities for transparency throughout the system, and there will be a step at the end where we want to correlate all of this together and ideally have one tool where users who want to verify their artifacts can simply say, these are the artifacts I care about for an ecosystem, and we can correlate across a number of different logs and verify all of the metadata that we need to do. So as a brief summary of the software development lifecycle, these are typically the 5 steps that we talk about. You have source, you have a build step. You'll then package your artifact. This is where you'll pull in dependencies, which also have a source and a build step. You'll distribute your artifacts, and then ultimately you'll have some end users consuming them. There's a number of entities that we have to trust throughout the SDLC. On one end, we have entities like SourceForges, GitHub, or GitLab. You have builders, and more frequently, CI/CD pipelines like GitHub Actions. Of course, at the packages step, you have dependencies where you also need to trust their SourceForges and builders. The distribution step is where we'll primarily talk about throughout this presentation, which is where we have package registries. These are central sources in an ecosystem, which makes it great to work with them when it comes to improving security of an ecosystem, because these are central sources for distributions. And then typically package registries will also ship package managers for end users to use to install packages. There's a number of different threats that we need to mitigate throughout the SDLC. And as you look at this list, you can think about where transparency makes sense to mitigate some of these threats or add discoverability, or where maybe it doesn't and we have to focus on something else entirely. We're going to primarily focus on package registries, and there's a few threats that I want to mention. One is the risk of stolen or leaked credentials, where a user's credentials are compromised and it allows a malicious actor to upload to the package registry. Another is malicious mirrors, where mirrors serve different content than what's in upstream. And another example is the registry itself may get compromised and end up serving different content than what's expected. So let's start talking about the process of uploading and downloading from a registry and where we can apply transparency. So this is the most simple example to start with. This is the typical process of uploading to a package registry. Some user is going to request an API key. They'll store that API key on a laptop. They'll build locally, and then they'll use that API key to upload.
But for one reason or another, this API key might get compromised. Maybe you install something malicious onto your laptop, it gets stolen, maybe you lose track of it, maybe that API key gets uploaded as a build artifact. These are real incidences that have happened. And at this point, now a malicious actor can upload a malicious artifact to the registry. Well, maybe you as a developer choose to switch to using CI, maybe just so you don't have to build on your laptop, or maybe you see it as a more secure environment because it's hosted. Well, it's the same setup here. You're going to have an API key. You'll store this instead as a CI secret, and then that API key will be used to authenticate to the registry. Well, in this case, you still have this long-lived credential, and it can still be compromised, right? We saw in an earlier slide that there were many different threats throughout the SDLC, and for CI workflows, one of them is misconfiguration. This was just one example that I wanted to highlight. There are many, many examples of this, but this was in a case where a popular AI repository, Ultralytics, was compromised through a misconfigured CI environment, and an attacker was able to exfiltrate a PyPI token for the Python package index and upload a crypto miner. So this brings us to one solution to this problem, which is trusted publishing. And the goal is to get rid of these long-lived credentials and move to ephemeral credentials where we don't have to worry about long-lived compromise. And the way that this works, it leverages CI workflows that are able to request identity tokens. So platforms like GitHub through GitHub Actions or GitLab CI also host identity providers. So when workflows run, they can request an identity token. And then this token can be used to authenticate to the registry. So there's an initial onboarding step where a user registers a source repository, or maybe more specifically a CI workflow. And then that token, which will contain the workflow and the source repository information, will be used to authenticate to the registry. This has been implemented in a number of package registries. One of the working groups that I work with published a guide for how this can be implemented. This has been rolled out in NPM most recently, but also the Python package index, PyPI, and Ruby gems. But as I said, misconfigured CI is still very much a real risk here, right? We've moved from long-lived tokens, where if an API key gets stolen, it can repeatedly be used to upload artifacts. But we could still have misconfigured CI that lets an attacker request an identity token, or maybe entirely compromise a source repository and release artifacts through this pipeline. So this is our first example where we can apply transparency. I work on a project called SigStore, which is focused on signature transparency. And what's great about this trusted publishing workflow is it's very seamless to integrate transparency into this pipeline, so we can have discoverability for when artifacts are published. So everything's the same here, except there'll be an additional step where the CI is going to request a code signing certificate for this identity. And the CI pipeline will sign an artifact and then upload this signature to a transparency log. So artifact owners are able to monitor these logs to know when their identity shows up. And if they have any unexpected cases, they know that there was some sort of compromise. And then this provenance will also be uploaded to the artifact registry, so any users can verify this provenance and any inclusion proof for this provenance as well. One of the other things to mention is what this identity actually is. So it's not like an email identity, it's a reference to the build environment where this happened. And what this ends up giving us is a cryptographic link between build and source. When we have one of these code signing certificates, we're able to look at the identity and go all the way back to the source code. So this gives us more auditability into the trusted publishing pipeline. And again, as we think about this end-to-end verification story, we're able to take a proof and take the provenance and go all the way back to source so that we're verifying what we're using was actually what was built from originally. So this is the first step along a process that we'll call transparent releases, where we want to add transparency throughout the SDLC. So what's auditable thus far? Well, the build process with signed provenance. But there's a number of other opportunities to add transparency to the upload and download pipeline for package registries. And
there's a number of questions we might want to answer with transparency. So one is the package registry publishing the same package that the maintainer intended? Is this same package being distributed to all callers, or is the package registry serving different packages to different callers? Are mirrors distributing the same packages as upstream? Are there any unexpected versions of my package? Maybe I published v1 and v2, but for some reason the registry is serving v3. Is that transparent? If provenance is present, how do I verify it? What's the expected key or identity that should be used to verify the provenance? And of course, thinking about this full end-to-end story, how do I as a maintainer make sense of all of this information? So binary transparency is very much a catch-all term. So here I'll define this as immutability and auditability for published artifacts. All consumers will receive the same artifacts given an artifact identifier, and we have a globally consistent view. Now, I don't need to talk too much about Go because we heard a lot about this in the previous talk, but Go is a great example of binary transparency with its checksum database that includes this mapping between a package identifier and a digest, which will guarantee that all users are going to download the same artifact given a package identifier, and it will prevent Go's module proxy from being able to tamper with artifacts. So we can generalize this process for any package registry. What's needed is some unique package identifier for an ecosystem. So one example is taking a package name, a version ID, and a file name. But this could be something else. It could be a URL, for example, as long as it's logically immutable. So for one example, in Git, tags are mutable, so those are not great as identifiers, though you could build a system that requires those to be immutable, for example. Each log entry will be a package identifier and its package digest. And what a proof means from the log is that there's a cryptographic commitment that a specific package identifier maps to a digest. So why are checksum databases great fits for registries? Well, one, they're very simple to integrate into the registry and tooling. As we've heard from some of the other talks, it's become a lot easier to operate logs. And so registries can host checksum databases, and whenever an artifact gets uploaded to the registry, they'll record this artifact in the checksum database and then store an inclusion proof that comes back from the checksum database. And again, this proof can also come with a witness checkpoint. And then tooling will verify these proofs whenever an artifact is fetched. What's great about this process is it's entirely seamless. It's invisible to consumers. The tooling is able to automate this whole process. There's no trust policy beyond what logs and witnesses are trusted by an ecosystem. So this is in contrast to something like provenance, where you need to know some identity or key provided out of band. The other thing that I really, really love about checksum databases is that we can enable them for all packages the minute that a checksum database is rolled out. Again, this is in contrast to something like provenance that requires artifact owners to actively participate, to sign and upload their packages. So we'll always have a long tail of packages that don't have signatures. But for a checksum database, whenever we spin one of these up for a registry, we can backfill it with all artifact digests that are distributed by the package registry, which means the tooling doesn't need any sort of policy to say some subset of packages might not have a proof. No, all packages in an ecosystem will be required to have inclusion proofs. So what are the threats that a checksum database mitigates? Well, one, tampering of any existing versions. This is because you would corrupt the log in doing so. And also, if you were to upload an additional mapping of a digest, an identifier to a different digest, this would be verifiable, and again, would invalidate the claims that the log is making. This also mitigates mirrors acting maliciously because they have to distribute the same proofs as what are distributed in upstream so that we have this globally consistent view. And this also lets us detect whenever any unauthorized packages are published. Now, this requires active participation from artifact owners, but what we heard yesterday from Martin with verifiable indexes, we have a path forward for greatly simplifying monitoring, and I'll demo that in a moment as well. All right, so that answers the first 4 of our questions for transparent releases. So the next one is, how do I verify provenance when it is present? So we said that each log entry is a package identifier and a package digest. Well, what if we also add the trusted publishing identity? And we can also imagine adding in any additional metadata that we might want to make discoverable. But for now, we'll focus on the trusted publishing identity. What this gives us is a way to audit any time publishing identities change. And it is expected that they might, a repository might be renamed, a workflow might be renamed. But we'll now have a history of this. And again, talking about verifiable indexes, we can create an index based on identity, so it's very easy to see where is my identity used, and we can also create indexes based on artifacts, so we can see identities changed over time, and artifact uploaders are able to verify that these changes are expected. So let's put all this together for a real-world example. And this is the proposal for what we'd like to add to the Python ecosystem. PyPI would host a checksum database. And the Python ecosystem already has a way to define package identifiers. So PyPI is able to host source distributions and also something called wheels, which are pre-built artifacts. There are specifications that define unique identifiers for these. So we'll use those for what gets uploaded to the package, to the checksum database. Now, for any ecosystem just starting out, they could also look at the package URL spec. So this is a proposal for how to standardize unique identifiers across ecosystems. Now, some ecosystems already have their own identifiers, like PyPI, but for those that don't, this would be something to look into. Potentially, it would let us build kind of a generic checksum database that would work across different ecosystems, but it's straightforward to build this for each ecosystem that comes along. So we don't necessarily need to standardize across all checksum databases with the URL. Users do need to know which identity. Again, this identity will be present in the checksum database, but they need to know which identity should be used to verify this. So for Python, we'll ship this in a lock file, which also contains all of the dependencies for rebuilding an artifact. On upload, PyPI will log an entry and store this inclusion proof. And then whenever an artifact is requested, PyPI will serve the lock file, the attestation, and this checksum database proof. And then a package manager will be responsible for verifying all the proofs and signatures. So that brings us to our last step, which is what should this all look like end to end? How does a maintainer verify everything that we've seen thus far? And I mentioned this already, but verifiable indexes are a great way to do this. It would let us answer questions like, did I release this version? Did I sign this version? Or what artifacts have been signed with my identity? So monitoring will connect all of this. And what I'd really love to have is one tool that simply connects everything given some artifact identifier. So it would let us verify that our artifact signing identity points to source. It lets us verify that artifacts are in the checksum database and the signing identity is in the checksum database. And we haven't really talked much about reproducibility, but if an ecosystem does support reproducibility, you also could use this identity to go back to source and then rebuild from source to verify that that artifact digest is also in the checksum database. All right, so I have a real quick demo just to show this all working together. So what I have running here is a checksum database. This is on GitHub, though this has a few changes that are just local right now. If you're curious about the technical details, this is using Tessera. I'm using the POSIX backend, so we're serving tiles just from a directory. I've got another script that's been running actually for quite some time that's currently backfilling this. I've put some aggressive rate limiting in place just so I don't overwhelm PyPI by trying to download all artifacts very quickly. But you can see this actively populating the local instance of the log. Now, in a real-world deployment, we could imagine that PyPI will just be uploading this. It's not going to have to parse a stream, but you could also imagine that an auditor could rebuild a checksum database based on this stream from a package registry and compare it against the checksum database that PyPI is serving. So I have here running two verifiable indexes. This is based on the code that Martin showed off yesterday. And then we can see here this working. So this is an example of looking up a Sigstr SDK that was written in Python. So you'll just see this running, and then this will dump all examples where this has been found in the log. So here's just one example. This is at index 113, where we have this release with this digest. And we also have an example where this included provenance. So we include the publishing identity. I can scroll all the way up to some examples where we didn't yet have publishing identities or provenance included for these before this was rolled out in PyPI. So you'll see an example here of that. And then we have another verifiable index where I can look up by identity. So this will return a subset of the list. Again, this will return just all places where we have found our identity used. And again, you can imagine this all kind of working together, but this last step, this is just running a tool to verify the provenance, which is also verifying the inclusion proof. You can see here, this is the repository, so this is effectively the identity that's used. And this provenance file also includes an inclusion proof from the signature transparency log. And if we run this, we'll see that it says this has been verified. So again, you can imagine that we could hook all of this together into one tool that makes it very easy for artifact owners to audit everything that they've published and signed. Alrighty, well, that brings us to the end. Thank you all very much. Any questions?
Any questions? No questions. Yeah, one question.
Thank you for the presentation. So you say that somebody could rebuild the same log with the feeds. Would they have to make sure that everything is received in the same order, or is everything ordered on the server side already?
You're right. You'd have to have the same order. So right now, I have not. I've just ordered everything alphabetically as I've been scraping it.
Oh,
so you would need the order. I believe there is a feed that is ordered by upload time as well.
Great. Okay, so that will work.
Yeah.
He kept turning off the microphone yesterday. It was a problem.
All right. Are there any interesting differences between using the checksum database for Go and doing this now in a different context of PyPI? Because I imagine they're slightly different. So did you encounter anything that was surprising or any new insights that you can share doing that sort of integration work?
It's a good question. There's not too many differences. So obviously Go has a different format for what goes into its checksum database, right? That it has both a checksum and of the module and also of the go.mod file. So this is a little different than in Python, where you have different artifacts that are being uploaded. So I would say that's one difference. And again, if we think about the end-to-end verification story and reproducing everything, that would look a little bit different. I do think this can be mostly standardized across ecosystems, just with each ecosystem making a decision on what exactly gets uploaded to the log. We'd still need monitors that are unique for each ecosystem, though.
Anyone else? Okay, well, let's thank Hayden again. And we will invite Holger to the stage to talk to us about reproducible builds, I think.
Hello, everyone. I will talk about reproducible builds, the last 12 years and the future. Also, I'm here to talk about the lack of transparency builds and how you can maybe help. So I'm a Debian user since many years. I work on reproducible builds since 10 years. I set up testing for many Linux distros. And I learned about transparency builds like logs 10 years ago, but never had time to dive into it further. So I'm here to present the work of many people. Three of these people on the list are in this room. And who knows about reproducible builds of you? Yay! So I can go home. Who contributed? Yay! Who knows that reproducible builds have been around for more than 10 years? Like for 30 years? Like the GCC toolchain was reproducible in the 90s and it bit rotted. And SBOM, the software bill of materials, is basically what we designed in 2014. So the problem is source code was freely available, but most people use precompiled binaries and nobody knows if they really correspond. And there are various supply chain attacks as a result. And so we have a definition: when is a build reproducible? A build is reproducible if given the same source code, build environment, and build instructions, anybody can recreate bit by bit identical artifacts. And this is a slide from 2014. So our mission is to enable anyone to independently verify that a given source produces bit by bit identical results. And so reproducibilities are an important building block in making supply chains more secure, nothing more, nothing less. Software which is unreproducible, which is unsecure, will stay unsecure, just everybody uses the same. And our mission, as I said, is enable anyone to independently verify that a given source produces bit by bit identical results. But what does that even mean? So we came up now with our new slogan, enabling supply chain security. It's way more clear this way. And by now, reproducibilities have been widely understood. We have many talks given, about 100. We have docs, publications, where various things are documented. The White House picked it up, the old White House, where they demand SBOM. And reproducibilities are an advanced technique in that. Yay, success. And to come a bit back, what it is that most people think software development is a benign, harmless activity, nothing can happen. But attacking software developers is very useful. With little effort, you can have big impact. And vectors can be really small. This is the actual SSH exploit. And there was one, it was greater equal, which is, or greater, which should have been greater equal. The diff is 1 bit in the binary out of 500 something kilobyte, 1 bit different, very hard to detect. And there are various other problems. So we tried to fix this, and what we found is mostly timestamps. Really timestamps, timestamps, timestamps everywhere. And the build path. And all the rest. And the rest is like we found 400 or 500 different classes of problems. And to tackle timestamps, and in there might be backdoors. Like the timestamps is harmless, but in the noise backdoors can be hidden. And so for the timestamp, we came up with source date epoch. Who of you know about source date epoch? Yay, some people. Build timestamps are largely meaningless, and source date epoch describes the last modification of the source measured in epochs since the Unix epoch. And so during the build, the current time is replaced with that, or timestamps are clamps, file times. And we made a specification like 10 years ago, updated once, it's been stable, and it's been used by a lot of software like GCC, various documentation tools, or various compilers, they all support it. That's pretty nice. And we developed Diffoscope. Who knows or uses Diffoscope? Yay, some people. So Diffoscope tries to get to the bottom of what makes files or directories different. It started with comparing 2 Debian packages, but by now you can give it 2 objects. I will have a list of what objects soon. And it creates text, HTML, or JSON output. You can try Diffoscope by just uploading it or installing it. If you install it with on a default Debian, it will install like 2 gigabytes of recommend, because it supports all these file types. You can give it 2 ISOs, 2 PDFs. Like lawyers use it to compare 2 PDFs to compare how laws have been changed. There are many use cases outside of software. And there's more file types. And there's fallback to hexdump comparison, fuzzy mode, lots of things. And we made summits, like we had 8 summits. And next week we have another summit in Vienna. If you're interested, you're welcome to come around. It's like a 3-day event. And there are many projects there who collaborate. This picture from that. So for Debian, we have partly reproducible builds, like more than 95% of all 30,000 or 37,000 Debian packages are reproducible. You can trivially create a base system which is reproducible, but we also have Docker images reproducible. We have live images, CD images now reproducible. That's all working. And this is the result, the progress in the last 10 years. So by now we are at 95%. The green one are the reproducible ones. This is really nice, and this was in CI with theoretically testing. On the way, we fixed about 4,000 reproducible related bugs. We still have some pending, and we found lots of more other bugs, because we constantly test Debian, rebuild Debian, like it's 11 bugs per day, filed and fixed by some people. And these were CI builders where we just rebuild twice and try to see, and we have maximum variations, so we build with different languages and different times and dates and things. But we also want to rebuild actually what Debian distributed. And finally we have done this, which is the new thing. There we try to really match what Debian distributes. We use the build info file, which describes the build environment and the dependencies and the results, and then rebuild it. And that works quite nice. For that we use rebuilder.d, which rebuilder.d is actually older. It was written in 2019, but Snapshot was broken until last year, until Linus and Glasklar and some Debian admins fixed it. So then finally we could set up this reproduce Debian.net. So the goal of reproduce Debian.net is to rebuild what Debian distributes, and this test setup is to try to find variation. And we'll keep this, of course we want to find this further. And rebuilder.d supports Arch Linux, Fedora, and Debian and Tails. And it's written in Rust. And you can install it either on Arch. It's soon available for Fedora as well. We have 5 instances for Arch, 5 for Debian by now, and 1 for Fedora. The Fedora part is still a bit in development. And for Debian, we now test all current suits, so the current stable Trixie, and all Trixie security, Trixie updates. But we also test Forky now. We test all architectures. S390 Access is pending. And soon the release team will use this for testing migration, so that Debian packages get uploaded to unstable and then migrate to testing, and soon they will only migrate if they're reproducible. So it is really, really nice. Arch Linux has the same, more or less. Also supports source.epoch, has build info support, and has the rebuilder instances sooner. And this is the web page. Some graphs. I'll skip a bit. I'm over time. You're waiting for lunch. So NixOS, by design, they say it's reproducible, but in practice they were not. I'll go a bit faster to get to the end. FreeBSD, and that has been tested, just the base system, and NetBSD as well, and then it stalled a bit. But last year, there was also the FreeBSD Foundation made an effort to do zero trust. And interestingly, the lower part, there's no transparency logs neither. So the reproducible builds world might be aware of transparency, but not really working on this so far. And how to reach 100% in practice? It's a political decision and nothing technical, because at some point we need just to say, if a package is unreproducible, we just don't ship it. We have 30,000 packages, and those 500 who are not, they need to be fixed. This overtime, how? Okay. So we can work around this by having allow lists, but in the end we want to get to 100%. Debian policy since 8 years says packages should be reproducible. And this is what will happen this year. Well, this year is almost over, but regressions will not be allowed anymore, and new packages need to be reproducible as well. And hopefully in 2 years we really say no. We'll see. And the release team will enforce this before it's policy. This is what I said. These are old numbers. And then there's more. There's Tor browser started it all like in 2012 together with the Bitcoin client. They were the first two projects which showed reproducible builds as possible. Tails is reproducible. F-Droid, Maven Central, the Java repository does support reproducible builds. And another side projects which are started from this were Bootstrappable.org, which does bootstrapping from by now a 400 byte binary seed, and what source compares what is in the distros compared to what's upstream. Transparency logs have been mostly out of scope for me and most people I work with as well. And I think we both could use both binary transparency and signature transparency, but we have neither. I'm here to collaborate and learn. I'm happy that you have me. I would suggest a breakout session. And I would like you to be the change, to become the change you want to see. And that's it. Thank you.
Amazing. Thank you, Holger. Do we have any questions? Over here.
So I think you said no to this, but are the remaining packages that are not reproducible, are they harder nuts to crack, or is it just because the maintainers don't care?
That's mostly probably harder nuts to crack, but you cannot really, it's LibreOffice, the Linux kernel, you name it, they are more reproducible. It's mostly small packages with annoying bits and pieces, and the number is still like 500 out of 40,000. But there's nothing really major. It's busy work. And most maintainers, most software projects really support it. Like the source state epoch shall be used if the environment variable is set. And GoScript is one exception where you need to set an environment variable that it should use the environment variable. But most other, just if it's set, then it works.
I'm actually kind of curious, how do you handle profile-guided optimization when you do reproducible builds?
I think I need to defer this to somebody else. I know this is a problem, but it has been tackled. But how in detail, I don't know.
You mentioned that it sounded like most of the work is upstreamed into the packages that are being reproducibly built. Does that mean that all the different distributions benefit from the work?
Yeah. It's often like when gzip or tar that give a parameter to make it sorted alphabetically. And then the next issue is to use local like C, because the different language sort different characters differently.
So how hard is it for another packaging system or another distribution system to gain the same benefits that you've invested into Debian?
It's easy. Like 90% we all have. Like whether it's Arch Linux has 95%, Fedora has 95%, and if you would start a distro, a new one, you will have at more than 90% as well immediately.
Okay, thank you, Holger.
Thank you.
No, I'll just talk for her. So now we have lunch again. Like people eat lunch every day. It'll be in the same place as it was yesterday. For those of you that were here, for those of you that weren't here, follow the crowd. It would be my recommendation, or follow people in anything that has this logo on it, because we know where we're going. A reminder, so directly after lunch at 2 p.m, we will be doing the breakout sessions. So if over lunchtime we've got a nice little selection of breakout sessions there. If you do have one that you haven't written up, do it right now. Otherwise, we get to play the dots game, if you remember from yesterday. If you can go and take a look at some point over lunch, you can either do it now before going down to lunch or after you've eaten. Take a look, decide which one you'd want to go to, put a dot underneath it so we know an indication of how big each group's going to be, so we can sort out where everyone's going to go after lunch. Other than that, see you back here at 2 p.m. for breakout sessions. All right, hello everyone. Hopefully you've had some productive breakout sessions. Please come and take a seat and we'll get started with some summaries. As you can see, basically we've been missing Martin so much. And so what we've done is we've managed to get a form of him here. And even though it's not as good as the real thing, we are still going to take him to dinner. So that should be a fun little adventure for anyone who needed more motivation to come to the dinner this evening. Martin, I hope you're watching. This is how much we missed you. Okay, if people can come and take a seat, we're going to do the summaries of the breakout sessions. Who would like to go first? Can we do the CT one first? Where's Joe gone? Did he leave? No. Who do we have in this room who's willing to do one of the summaries from... Oh, yes, there you are. Okay. Handing over to Joe for the summary. I will take Martin with me.
Oh. You like the company? I mean, no, that's okay. He can go back later.
Oh, we'll put him over here while I hold on.
Excellent. Please excuse me for a moment. My memory is terrible. All right. So, we had a good conversation about CT, as we often do. We had a bunch of different topics that came up in our not nearly long enough session. There's a proposal on CT policy right now about making it easier for, mostly for user agents, to automate the inclusion of new logs submitted by log operators. And we had a good conversation about how folks were feeling about that and whether the scheme was okay or something that they were interested in enacting. And the real push for that format is because it would enable a lot of automation, which would in turn let us have shorter temporal shards for CT, which would be useful since we now have, or we are going to have, shorter and shorter certificates, which means a higher volume of certificates, which means larger logs. And so it's nicer to have shorter lived logs so that you can reclaim that disk space and reuse it. So we had a good conversation about what sort of world we would like to live in once we have even shorter certificates and how short the shards should be. And the short answer is you can do all sorts of fun stuff as soon as we start automating all this because it doesn't really matter if there's not as much human involvement. We had a conversation about the policy that Apple and Chrome require right now where the SCTs presented to the UA have to include at least one SCT from a 6962 log, RFC 6962, rather than purely from static CT API. And we were discussing a bit about when might be appropriate to remove that requirement and the criteria under which we'd feel comfortable doing that, which was like, is there adequate support for this new spec among monitors? Do we have adequate confidence in the static CT API log implementations, that sort of thing? But I think that's on the horizon. We had a good conversation about how much interest there was in CT for adopting witnessing more broadly than we do right now, and sort of relatedly, how much we want to treat CT as in maintenance mode versus how much do we want to iterate on it and improve it. One approach might be to say, okay, CT is actually in a pretty good spot right now, so let's keep things where they are, and then we can bring our focus onto Merkle tree certs or whatever happens next for a PQ world. I think there are strong arguments on both sides to that, but there does seem to be some interest in sort of doing for the write path, what static CT API did for the read path, which is to say, how can we optimize to be easier for logs to serve and that sort of thing. We also had just a couple of minutes of talking about a hot topic in CT, which is how much garbage should we expect logs to accept? And what we mean by that is it's a very nice property that in CT right now, to a first approximation, if a CA issues a certificate, even if it's malformed, there's a good chance that it will still show up in CT so that we can all collectively see that behavior and then ask the CA to do better or similar. And at the same time, that's a real burden for log operators or logs and log implementations that want to, for instance, not support SHA-1 forever, or whatever the thing is, or need to deal with every conceivable malformed version of certificates and how to handle that balance. There's a fun idea floating around of having essentially a log that does nothing but store garbage that the other logs weren't willing to accept. And there are interesting questions there of like, well, how do you build a log that'll accept damn near anything without it becoming a source for something that could be trivially DOSed with just throwing infinite garbage at it or whatever else. And also, how do certificates end up in that log? And that, for instance, would require logs when somebody makes a submission to them where they get an entry where they're not willing to accept it because they think it's garbage. They need to forward that entry on so that it ends up in the garbage pile with all the rest of the garbage. But yeah, some good fun conversations for CT. That's all I got.
Right, who's next? Who do we have? Yes? Julio with the web. For some reason I can't remember the second word, but the web group.
Hey all, we had a very nice hour of discussion. We first talked a bit about past mistakes, like public key pinning in the browsers that broke everything, and now not to repeat mistakes of the past with whatever we came up with. We discussed a bit about how HSTS works and how we can draw kind of inspiration from the past versions of some of the features we are trying to build. And then we discussed a lot about the threat model and what kind of use cases are we going to try to serve and how to balance security properties with availability so we don't repeat the HPKP mistakes, meaning that how to prevent websites to stop functioning for whatever reason, and probably how to prevent the blame to browsers when that happens. Then we discussed a bit the log structure of the WCT proposal. And it was mostly that we went through possible use cases, like what the various applications that right now are interested in transparency or other things. What requirements do they have and on which security they rely? Could they afford downtime in case of incidents? Like when is it fine to decide that a website is insecure and so you would privilege the security over availability, and all these kind of things that try to bring stakeholders together to produce probably a standard that works in most cases.
Amazing. Okay, who's next? Which one of the group leaders? Yes, the Teletis people. Looked like you were having lots of discussions.
Yeah, we did. It will be difficult to sum up because we used the breakout session to break up in several groups. So I think we were like 6 or 7. But we had like open questions about what we can do, feedback on the hardware, on the thoughts that we have for the HSM. And I hope my colleagues had good discussions with all of you. And we'll see what we'll take it from there. Thank you.
Yeah, when I asked him to do the summary, he was like, but everyone's been talking separately. We don't have any. And I was like, go up and say that. So great. Okay, who is left? We have the academic group.
Yes. Thank you. So we had a lengthy discussion, but I will keep the summary very short. We talked about 3 things. First of all, key transparency. We like it. It's tricky, especially if you want to combine it with like a privacy-preserving way to access your key, or so that the KT's server doesn't know who is querying, so that cannot target use attack. Second, we talk a bit about end-to-end encryption, and the discussion was rather brief on this because we all like it and we think that should be, used. Preaching to the right choir, right? Lastly, we talk about chat control, and everybody agrees it's really bad. And I'm not going to state why here on stage, but please come to any of us. I think we can have a very long discussion regarding this new directive that Europe is trying to put up. So if you are not aware about that, please come to me or anybody on my table, and we will be very happy to inform you on this crap.
That's technical terminology there at the end. And then reproducible builds. Oh, yes.
Hello, we were 5 people, and somebody was there who was using Geeks, and I forgot to mention Geeks. Geeks is basically as Nix, and also forgot to mention SUSE, and SUSE has a 100% reproducible prototype. I wanted to mention this. And then we talked about transparency logs. Filippo had yesterday offered to set up a log, and Linus mentioned that we could just use an existing log. We discussed that at first wanted to log binary packages. In the end became that we rather want to log keys for the release files. And we talked about the need for witnesses. And then we concluded that we end this by setting up a wiki page to document this. So this is the wiki page where we document what we want to do.
Awesome, amazing. So yes, it seemed like, again, as with yesterday, everyone was reluctant to break up the breakout sessions. So it sounds like it was another very good use of time. I have heard from Martin. He has witnessed this, and he's finding it funny, so that's good. The next we have just one talk under the umbrella of identity systems. So I'm going to invite Alexis to the stage to talk to us about that.
Hello, everyone. And I'm going to start a timer on myself because I need that. So I'm Alexis Hancock. I am from the Electronic Frontier Foundation. My day job is mainly working on an Acme client called Certbot. You may be familiar with it. And do I have a clicker? Yes, I do. But I'm not here to talk about Certbot. I'm not here to talk about the more fun things that I like to do in my day-to-day job. I'm not here to talk about Acme or TLS or any of those things. And if you have problems with Certbot, please file an issue. I am not a help desk. Please don't crack up your laptop and show me your certificate configuration, please. I'm here to talk about digital identity. This is something that I've been on since 2019 when I went over the draft for verifiable credentials, and then when I went over the draft for MDoc, which rules the mobile driver's license standard. It's here for better or for worse. You may have heard of it. Different countries have different implementations of digital identity. In the US context, I want to say about maybe almost half the states have some sort of implementation of mobile driver's licenses. So it's here. Whether or not you think it's a good thing or a bad thing, it is present. And in most digital ID systems, you have 3 roles. You have the issuer, the verifier, and in some contexts, people will say the verifier is a relying party, or you'll have the holder or the bearer of that said credential, right? So presenting your ID online is not the same as presenting your ID in person. The most used example that I have seen is when you go to a bar and you present to the bouncer at the bar your ID of some sort of kind of, verification that you are the age that you say you are. They see a lot of information on it. They may see your address. They may see your classification of what you are and what privileges you have to drive with, other things of that nature, right? And that is considered privacy violating in some point because you're just trying to prove your age. You're not trying to prove anything else. But the problem is this is not a one-to-one application when you go online. It's not just one entity involved of looking at this possibly overdone amount of information for a particular use case. Going online means you are calling for an entire system to be sound, to be accountable, to be transparent, and mostly what they're calling for is some sort of PKI system online between these 3 parties to be able to use your ID online and present, in a lot of contexts in recent laws and things that I've seen in different countries, your age. Issuers and accountability, what does that look like in these systems? So obviously there needs to be some sort of PKI for issuers, and that's been mainly solved in some context of how an issuer can issue a digital credential of some kind. That part has been discussed in depth, and there are different methods and ways to do that, to provision someone some sort of license or digital credential that reflects their ID in real life. And also responsibility to the holder and the verifier to make sure that this credential is not able to get tampered with. What does this look like for holders and choice? There's not a lot of choice holders have right now in many of these systems. I've been evaluating different systems around the world. I haven't seen much given. The government usually chooses what kind of wallet implementation that you're going to get. For example, in California, in the US, they have partnered with Google and Apple Wallet. They have partnered with a different company called Spruce ID to build the application that holds an MDL as well. You don't really get much choice or say as a citizen in these types of contexts, or as a person who has these IDs and wants to get an MDL or a digital credential. Presentation choice is not really a lot of options around that either. If you're a holder of that said credential, if I want something as nice as zero knowledge proofs to be able to present my age online, I can't just go to the implementer of my country, state, or wherever I am and say, I want it done this way. There's not much choice to the holder there. When I have seen these systems come into play, it's usually what the government says, with how they're going to implement it. And there is some talk of interoperability, but I haven't seen much deployed just yet. What does accountability look like for verifiers? So we have the EU ID, where verifier registration certificates were being discussed, but that has been since then rescinded. Maybe it will get added back as a provision and a requirement. I have not seen it yet. Apple's ecosystem for digital credential API, which is through, I want to say, the W3C, but Apple and Google Wallet both support digital credential APIs. And its implementation in Apple context is you use Apple Business Connect to as a verifier in this ecosystem. So that gives some sort of integrity check of some kind on the verifier within their ecosystem, though. Then there's ISRG Research, or the Internet Security Research Group. You may be familiar with them. They also did some sort of consultation work in the ecosystem in the context of the EU ID of whether or not, in the more reactive sense of if a verifier is requesting certain types of information, possibly using a privacy preserving way to track that and what type of information relying parties or verifiers are collecting. And that is more on the flip side of what I've seen with verifiers. It's more reactionary, and also not a lot of things I've seen around keeping them accountable otherwise. Possible tool, verifier transparency logs. This is something that I am not married to as an idea. This may be a bad idea. This may be a good idea. Feel free to tear it apart or say it's a good idea. For verifiers and their intent, I am not quite sure whether or not this will be something that will be useful, but I do think verifier transparency laws could proactively slow the flow of entry point of unfettered verification just happening overnight. I do think there should be some sort of barrier to become a verifier in a system that exists to help you at least onboard verifiers into a system and be transparent, auditable, and be able to keep track of it. Wallet creators could even actively be witnesses to these logs or become log runners themselves. Holders could be able to at least utilize these things to cross-reference with people who are witnesses or entities or organizations who are looking at these logs and able to cross-reference any sort of abuse, especially when an verifier had put out an intent of what type of data to collect. Say, I'm only going to collect age, but then holders are reporting, actually this verifier is collecting age, my name, my address, and other information on my ID. So this is just something that I thought about. Alexis, who would run these logs? I don't know. This is all coming out of my head as something to be more proactive around verifiers and keeping them accountable. I do think maybe potentially wallet creators, or it could be other entities and organizations that are oversight bodies on verifiers in particular. This is something that I've thought about in length in terms of making sure that there's some sort of power distribution back to the holder and some sort of accountability back to the holders of these credentials. Because right now I have not seen a lot of shift and balance of power back to them, because a lot of the public is being asked to be burdened with just trusting these new systems and hope that they go all right. And I would like for that, some of that distribution be put back to the holder. Thanks. My email if you have ideas, and this is a link to EFF.org if you want to support our work. And that is me. Thank you.
Great stuff. Oh, hello. Hello. Yes. Questions for Alexis? No, none. Yes, good. Every time I say that, someone puts their hand up. I'm learning the tricks.
Hi. I'm aware how these things are in Sweden, particularly, and for us, it's a problem that to use the digital ID systems that are in practice used for almost everything, you have to have a certain kind of device. In practice, Google, Apple, Microsoft. If you don't have those, then it's like you're almost not allowed as a citizen. That's, legally you don't have to, but in practice you have to, right? Have you seen how this is in other places?
Yes. So right now, the biggest worry that I have is around mandatory age verification, because this immediately locks out a lot of people who don't want to participate with certain ecosystems or have issues or reasons around privacy. So Persona is a company being used in the UK right now for age verification. And when you slide digital identity into these systems as a mandatory mandate of some kind, and having a mandate around that and having tech mandates, you do lock out people who can't be a part of that specific technical ecosystem. So that's why I'm thinking about diversity of methods and things of that nature to be able to fall back, because these systems will fail. And what happens when these systems fail? And you're going to need a fallback. So that's why we're fighting for things like EFF is like a right to paper, and being able to use that physical documentation if you need to. And if you want to let citizens participate in a digital ecosystem, they can, but it shouldn't be mandatory. And there should be fallbacks and other options around that, because if it's really about access, then it should be about access from all points of view in your country or member state or wherever you are in your jurisdiction. So that I have seen that come into play, especially people who don't want to participate in like Persona in the UK and just automatically agree to their terms and services and their privacy issues as a company, just to participate and be able to see some content online that they yesterday were be able to engage in without having to show their ID proof.
Yeah, thank you for the talk. As you may already know, the age verification thing from UK is already in some ways splitting the internet. Mm-hmm. There are services that works no longer in the UK. And digital ID is also a matter of national security or sovereignty, with states that will want to participate in, at least in the choices that are being made. And so is there like some kind of international initiative around digital ID, or it's just some ways that the internet will be broken apart by states, and that?
That will be up to the lawmakers and those legislators if they actually listen to us. There are various governments around the world thinking about this, and they are, in fact, participating in various splinternet practices when they do this. There's already a law recently in the past 48 hours that's come up in Wisconsin in the U.S. to ban VPNs to keep people from actually being able to access VPNs and ways to circumvent their potential age verification law. So these are various splinternet practices that we are concerned about. And the hard line at EFF is that we don't want these mandatory laws to come into effect. And we understand that that's happening. A lot of it is a defeatist attitude that we're pushing against the tide. But if we had a defeatist attitude at EFF, then I wouldn't have a job. I shouldn't be here. I shouldn't be on stage. I should just give up and go home. But I'm not going to do that. I'm going to keep talking about how these systems are not scaled out to handle this sort of thing. There's different people, different contexts in different countries that have different status with identification, whether or not they're undocumented or just had issues just obtaining valid documentation for whatever reason, right? So it does definitely push out people even within your own country and within your own jurisdiction, let alone people from other areas. So yes, it's various splinter net practices at play, and people don't like being compared to other authoritarian regimes and things of that nature, but at the same time, like, technically it looks the same. So you have to confront it for what it is.
Hi. I have more of a comment rather than a question. I thought I'd just use the attention span of the audience, given that we're all talking about digital identity now. Transparency logs for verifier certificates is actually a thing that's considered, it's actually a thing that it's required by law now in the EUD wallet, European Digital Identity Wallet ecosystem. It is about authentication certificates, not authorization certificates, so not the scope of attributes that's being required by the verifier. The only problem is that it is being sort of copy-pasted from the WebPKI ecosystem to the Digital Identity Wallet ecosystem. So if any of transparency specialist experts wants to contribute to the discussions, there is a GitHub topic open for discussion. There is a draft that you can still provide feedback on, available.
So the requirement has been added back?
As I said, it is about access certificates, which are authentication
access certificates. Yes.
On the registration certificates, which would be about the scope of attributes that a verifier is allowed to request. It is right now in the law, it is optional, but member states can override it. And countries like Austria, for example, for them is mandatory, and a few other countries as well do have it as a mandatory certificate, and it will be presented in the flow between the verifier and the wallet when the verifier asks for credential presentation.
And I do believe ISRG brought up access certificates of being able to use the privacy preserving methods of being able to use the telemetry from that access certificate to be able to see what they're collecting. But I do remember that term in that discrepancy. So thank you.
You're welcome.
Okay, amazing. Any more comments, questions on what is actually a very relevant topic at the moment? No? Okay, well, a big thank you to Alexis for coming in. She joined our agenda quite last minute, and we really appreciate it. Okay, so next, I'll go up here again because the speakers, I can hear weird things. Next, we have a break, Swedish fika break. We will come back at 4 p.m. for the binary and firmware transparency session. A reminder to all speakers in that session during this break to come and get mic'd up. Also, for anyone who didn't get a t-shirt, if you would now like a t-shirt, we have some left over. Come and see me during the break. We will see if we have your size, and you can have a t-shirt. Other than that, enjoy your break. Nom 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 nom. Hello, everyone. Welcome back. If people can come in and take your seats, we're going to get started on our final talk session of the day. We have a wonderful looking lineup. Oh, with some fun names. Not people names, technology names. Well, also fun people names. So to begin the binary and/or firmware transparency session, I'm going to hand over to Andrea and Daniele to talk to us about. That's quite long. They'll tell you what it's about. Enjoy.
Something. Can you hear me? Yeah. Hello, everyone. I'm Andrea. This is Daniele. Work together at the ReverseSec product security team. So I think Daniele kind of had the impression that this was like kind of a dragon's den, very scary environment, that you are all going to be judgmental. This is his first open source transparency project. So all of this, like 99% is his work. So be kind, because I told him that you're a nice community, nice group of people, and that you don't bite, and only good can come out of this presentation. So yeah, I'll talk briefly at the end, but now give it to Daniele for this. Yeah,
that's actually the first conference, where I feel that there are smart questions. So it's like very unusual.
They're
right?
all smarter than you. Don't worry about it.
Yeah. Okay. So let's do a step back. So I'm here today with Andrea presenting how we started implementing transparency into UEFI boot managers, UEFI bootloader. Okay, the usual who we are in this case.
We like ASCII art. This is the future.
No, jokes aside, I like very much this diagram that Andrea actually did, because it's a condensating, our history. We used to have a company, our own company, which are still very proud of that, was called InversePath, that then it became acquired by F-Secure, that then became SweetSecure. Now it's eventually ReverseSec. But it doesn't matter to us because we are still, a small island within this bigger entity now. As Andrea already said, we are the ProdSec team, which, we are doing a lot of different activities related to hardware, firmware, software, penetration testing, research, blah, blah, blah.
But we get to hack compilers and also do security
exactly.
Which
But
is what we love.
I don't want to make long story short because otherwise we
have 25 minutes.
Rush. This slide.
Chop.
So if you see the open source part of the diagram, there is that, Tamago central component that Andrea will talk a bit more later on. And then there is an appendix, right? Go boot, and then finally boot transparency, which is the topic for today.
It's going to make sense.
Yeah, it all makes sense. Yeah. So boot transparency is a pure Go library, basically, which enables interaction between the transparency infrastructure, the transparency ecosystem, and booting operations. Let's say, okay. So it allows you to be selective in what you authorize or not for boot, depending on a policy. Okay, so there is policy enforcement on the boot artifacts, and then if whatever has been claimed for this bundle of artifacts is matching the policy requirements, then you go on with the boot. Otherwise, the boot is not authorized. And one important aspect of the whole concept is that it needs to be robust enough to be reliable even in full offline situations. Then if you have networking access, then you can do steps further. So this is the whole idea.
And the basic concept is that we want to bring transparency concepts and expand from this usual notion of a binary secure boot environment, whether something is authenticated or not, and that's it, which is what you get with secure boot, and also trusted and measured boot, which is somewhat something that in certain environments just cannot happen, and also has its own complexity and legacy, which is not quite, I think, modern, at least in the way we think.
Yeah, exactly. Yeah. Architecture. This diagram tries to glue together, all the pieces which are involved. So you see there is the submitter in the center of this diagram. It could be the OS distributor. The entity which is distributing the boot artifact, the artifacts bundle. Then it is logging to the transparency infrastructure, to the transparency log, a set of claims about the artifacts, like there is a kernel inside which is version blah blah blah. It's not tainted. It has been built with this and that option blah blah blah. There is an init RAM disk which has been built with this option. It is version blah blah blah. It is not containing any tainted module and so on. The log.
Is there a constant for blah blah blah?
Okay.
You just enumerated that a lot. Sorry, go ahead.
And the
comic relief.
It is disturbing. I'm already late. The transparency. The transparency log is responsible for doing the transparency business, of course. Then there can be monitors behind him, monitoring that is behaving correctly. And important thing, there is the witness network on the other end, responsible for doing the classic witnessing activity, which is fundamental in our context for preventing split view attacks and so on when we are especially when we are in the full offline situation. Then basically the submitter is now time for him to publish the artifacts. Then it will publish the artifacts plus the whatever is the transparency proof bundle. And then on the other side, there is our bootloader, which has embedded or it has configured a certain booting policy, which will decide whether to authorize or not the bundle of artifacts. This is also true. Boot Transparency Library is a pure Go library, which eventually could be used not only in bootloader, which is the most interesting case we are presenting now, but it can also be used in a user space installer, so in a user space tool. And then, of course, in that case, the believer is the installer. And in that case, the action will not be authorize the boot, but it will be, for example, install the artifacts, for example.
It could be even other distributions that just need to package a kernel that was made by someone else, for instance.
Correct.
So it doesn't. The context is irrelevant to the boot transparency, even if we're going to provide a specific example.
Yeah. And on the other side, to make everything, let's say, useful or really powerful, of course, we do need advanced monitors that in theory, they would have to have access to the artifact bundles, but also to the inclusion proof at the same time, exactly how the bootloader has. And this is needed to verify, eventually, to go deeper the crust of the transparency layer and to being able to judge whether certain claim is true or not, or whether basically certain claims originally made by the submitter are still valid or not. But we will go a bit deeper in this later on. The design, I think I already, pretty much told everything.
I think the key point only here is that it supports multiple transparency engines.
Correct.
So they're pluggable. So right now we have code for SIGSAM and Tessera that Daniele made. So I think that's...
I will jump into that later on. But that's true. I mean, the flexibility of having multiple transparency engine support and also the concept of having multiple artifact categories supported is something that I will discuss later on, because it's pretty central in the way we develop the whole thing. In terms of model, I think also I already pretty much spoken about this, but just for the sake of being more clear, there are claims about the artifacts, about boot artifacts, artifacts which are included in the boot bundle. Then there is a statement, what we call statement, which is the set of claims made for this boot bundle. Claimant is the OS distributor, the entity which is releasing this boot bundle. the believer is either the bootloader or eventually the user space tool or whatever tool which believes on those claims to take decision on the boot bundle. The action, how this bundle is authorized or not for boot, or this bundle is fine for installation for the update of the kernel or not, blah, blah, blah. Then verifier is where things became more, maybe gray area in this moment, because there's still, it's a working process, right? It's not something production ready. Verifier is like whatever entity is responsible, whatever entity is able and responsible for going into the claims context and judge whether a certain claim is correct or not, and eventually generate, an alarm or some sort of information that then could be reused by the believer to decide, how to proceed in its action. Again, transparency engine, we do support multiple transparency engines. In this case, right now it's SIGSAM or Tessera.
Yeah, but the API is abstracted, so there, it's from a user perspective, it doesn't really matter.
If in the future.
Yeah.
So I don't know, but yeah. In terms of proof of public logging, everything has been built starting from what is the SIGSAM verifying proof documentation. So we are still keeping that logic, which is then fully applicable also for Tessera. There is nothing interesting probably for you here. Just the fact that we are supporting witnessing from the very beginning. And again, because this is quite relevant for mitigating split view attacks, especially when we are in a full offline situation. And the nice thing about the latest updates in Tessera is that now we can reuse exactly the same witnessing policy format directly from SIGSAM. We can now start a new witness group in Tessera, and then we can ask this witness group is satisfied or not, and we can just throw directly the SIGSAM format, and which now is fully supported also by Tessera. So this is very nice. Tessera, by the way.
We're Italian, so we should be able to say Tessera.
Yeah.
Sorry.
That's quite true, but it's the Tessera. Okay. Anyway, artifact categories, we do have this abstraction layer from the beginning, because at the early stage we kind of realized that but it will happen sooner or later that we will have issues in parsing or let's say in having code which is specific to a certain artifact category like Linux kernel or an init RAM disk or a DTB and so on, because clearly what you could claim and what you could require in terms of policy for a Linux kernel is quite different from what you could be interested into claiming or requiring for a DTB or a WEFI binary or whatever it is. So there is this abstraction layer in the middle. So in future it will be quite easy to add new artifact categories and so on. So this is the whole.
Is that anybody can, we can sync on the IDs that are defined, but we could import libraries from, whether if you're Lenovo or Dell and you want to find different categories, it's possible, or if different operating systems, and the library allows to register arbitrary handlers for IDs that are not like the prime citizens of our library. So anybody can just add them if they wanted to. So.
Yeah, that's the idea in mind. Yeah. So just an example of a potential booting policy, very straightforward example. Now we have this boot bundle. We do. If you want to be able to boot, to have a Linux kernel inside, which is at least this version, then it must be not tainted, and then it must be, in this case, compiled with config stack protector strong option. And it must include an init RAM disk, which it does not contain any tainted module. Just very simple example. Aside this, we do require that these claims have been signed by at least 2 among our trusted signers. And this quorum, it's not related to the witnessing quorum, okay? Just for the sake of clearness, here we are at the policy layer. So it is a way to define a signing quorum despite whatever it is happening at transparency layer, okay? So it's a different quorum, it's not related at all to the transparency witnessing quorum. Here we have other examples of potential policies. I don't want to waste too much time. This is just an example of how we can, implement fallback situations where, for example, okay, but how you could realize a policy, how you can create a policy where no matter what it happens in terms of Linux kernel or whatever, I can still boot if my trusted init RAM disk is present and so on. So it's just a fallback scenario. Aside the library business, we immediately realized that you also need some tool to actually use this thing. At least you need a tool to kind of be able to parse the statement and ensure that they are consistent before actually publishing or deploying the stuff. And this tool is also signing, the statement for the quorum I was talking before, and it is also verifying signatures. So, okay. Symmetrically, we do have kind of the same tool for the policy, so you can parse the policy before actually deploy it to ensure it's consistent, and you can do the check of the policy against the statement you prepared before to ensure that they are matching if you are expecting they are matching before the actual deployment. And finally, there is sorry for my fantasy, but BT, it's boot transparency, BT bundle. The tool for create the final bundle, which is the only single JSON file that at the end, along with the policy, it's going to be shipped to the bootloader. So the bootloader at the end, the idea is that at the end it has the bundle of artifacts on one side, and then this BT bundle, which is including the original statement, the proof of logging, and also some probing data in case you want to retrieve a fresh inclusion proof directly from the log.
So a naive audience, which is not you, but a naive audience might ask, how the hell am I going to use a Go library which is doing all of these things in a bootloader? Because bootloaders are written in C, under UEFI, becomes complicated to import these libraries. You could write them in Rust, but still, I don't think the ecosystem is mature enough. And that's where Tamago comes in place, which is our Go compiler modification, which we mentioned before. A lot of you know about it, and I'm very pleased about that. Which now targets also x86-64. This is something that has been introduced February of this year, and we created Tamago support for UEFI. So now UEFI boot managers and EFI application can be created as regular Go applications. And this is what enables using Daniele's works in the context of a pre-boot environment, which otherwise would be pretty difficult to do. So we created Go Boot, which is a UEFI boot manager, can boot Linux, can boot Windows, has a library to interact with UEFI functions. It's very compact, 2,000 lines of code, and it also has networking support. So it can use Go networking, TLS, HTTP, all of the goodies, and also Daniela is going to do a demo for that. And to me, it's also a way to rely less on UEFI primitives. UEFI is a big monster which has a lot of functions that helps C-based EFI applications to do things that otherwise are difficult at that boot stage, which is TLS networking and cryptography. But by bringing Go to this environment, it means that we can use every single package that you can think of in Go without having to rely on UFI. So networking stack is gvisor. We use NetTLS, NetHTTP, regular expression, because UFI also has an API for regular expressions inside. And if you want to use Tailscale or WireGuard in your boot manager, you can do it. And this is what enables using Daniela's libraries in this context. And so one of the things that Daniele was able to do is just to develop his own library, and correct me if I'm wrong, in a complete user space environment. Yep. And then it was simply cut and paste into a UFI boot manager, and it would just run in a command that we do in GoBoot. So now I'm going to show the demo.
Yep. Yeah, that's exactly what happened here. It's just cut and paste.
What Daniele is going to show you. So of course now we cannot show you the laptop booting, so we're going to use QEMU, but it's going to look exactly the same on for instance, my laptop when I boot it up. So this is the UFI shell that we implemented with GoBoot. Daniele is just configured networking now. So this will use the UFI simple networking protocol, and we will hook up gvisor, which is a full Go TCP IP stack, to the network. And so now it just SSH to the bootloader, which I think is amazing. And everything that's happening here is from SSH and all pure Go. It's listing the file system. We bridge the UFI file system protocol with the Go IOFS interface. So again, from a developer perspective, it looks identical to the same code developed for Linux or Mac or Windows. So now is showing the policy. We are in the bootloader now. Just remember that. This is not a Linux console. So this is the policy that is in place right now.
That's the witnessing.
Witnessing policy. Yeah.
And then what else? That's it, right? No, if you want, I can also show you
LS. Otherwise, you put Linux.
Yeah.
Yep.
No, I wanted you also to show the. And this is the BT.
All of this lives in the EFI partition, by the way.
Yeah, those are the files that are seen by the Wi-Fi bootloader. Okay, so we have the booting policy, which in this case it's super straightforward. It's like, okay, boot again. It's the same policy I showed you before. Like it needs to contain at least one Linux kernel which is matching this version, not tainted, and having the config stack protector strong, yes, and then an init ID with that, and it needs to be signed by at least two among these two, in this case, signers, okay? The witnessing policy, blah, 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 blah. Okay, let's jump. And
all of this could be retrieved by the network because we have network support. It just so happened that in this case, we take it from the file system.
And now, okay, if I do the boot,
yeah.
It is basically connected to the remote server now using the network. It downloaded the inclusion proof, and now is evaluating whether the claims are matching the statement. All good. Boot is allowed. Jump in the kernel. It loaded the kernel. Okay, IO error, but it is boot.
Everything happened in an instant. The only delay that was there was actually booting the kernel itself, because the file system that QEMU emulates, it's a little slow, but it was absolutely super fast, happening faster than the equivalent code running under Linux without an operating system.
And now, okay, the vice versa. I commented out the policy that you just seen, and then it's policy unauthorized set in the command, which is the same policy, but instead of asking for a correct metadata, is asking for I want candies. Okay.
This boot manager, by the way, being a Go binary, is perfectly reproducible. Of course, it benefits from all the ecosystem that you enjoy from the Go module and so forth. You're missing the CIDR prefix over there, yeah.
Now, yeah, I think.
And there's a space missing there.
It's typo day.
Take your time. Take your time.
It's
just
not
over time by 4 minutes.
Yeah, but
don't worry.
It's not because it is because today it's the day.
Yeah,
of typos.
yeah. It's fine. It's fine.
I mean, I could be. So yeah, if I do the same boot now, it goes. It downloaded the fresh proof. Then it was checking the boot transparency policy. Okay, claimed string is not included in the requirement because of that. I want candy.
Good.
So yeah.
I think we jump straight to questions since we're 4 minutes over time.
Yeah, the presentation is pretty much done actually.
Of course, there are improvements that in future we can make. This is all public on our GitHub repository. We have the links later on. But yeah, I mean, the reason why we're here presenting it is because we want to hear your feedback, understand, how we could improve this, what we're doing wrong, what we're doing right, and yeah, generally to have a discussion about it. So, thank you.
Thank you.
Wonderful. Do we have questions? Yeah, I know they've mentioned they're a little bit over time, but we do have time for 1 or 2 questions.
I'm going to ask the obvious one. How hard it is to migrate to this from, for example, group or other WEFI cells?
So I have to be honest. I mean, yeah, to be honest, you saw that diagram, right? Now for us, this boot transparency, it's an appendix of GoBoot, which is yet again an appendix of Tamago, which is our building block, central building block, right? So everything has been made, as Andrea said, it has been developed in pure Go with no knowledge whatsoever about GoBoot, about Tamago and so on, and then it has been cut and pasted into GoBoot, and everything worked like after probably 20 minutes or so. Now, this is true for GoBoot. Now, your question, we in the team there is Andrea, and also Andrei knows very well other bootloaders, U-Boot, and so on. But the thing is that we are talking about a pure Go library, so all of this really makes sense with GoBoot, right?
But I think the question was how to replace Grub with this, right? Yeah.
No, to integrate or
no.
No. Okay. Sorry, I got how to integrate this in
GoBoot. Already works on all UEFI-based targets, and we do parse the same configuration format of systemd boot. Just because I use Arch Linux, I use systemd boot, so I wanted GoBoot to boot exactly the same boot entry that I have. So I guess it's easy to port those configurations, right? Concerning this library, I guess it's just a matter of building the ecosystem around it for making sure that the log and the claims are available. But as far as the bootloader goes, it's already worked. It's booted my laptop and others. It's very easy. You can roll it up today if you want to. It's production ready.
Yeah.
Does that answer your question? Yeah, thank you.
Okay, with that, we will have to leave it there. Do feel free to have more conversations with Andrea and Daniele.
Thank you.
Separate from this, but we need to move on to the next talk now. Thank you so much.
Sure.
So next we have Tom, who's going to talk to us about binary transparency via endorsements. And I believe he's joined by someone, Ben? Someone called Ben. Who's not on the schedule.
Okay, great. Hello, everyone. I'm Tom. I'm from Project Oak. And this is, I'm going to talk about what we do to our binaries, being on the edge of open source and proprietary things. We have some special instrumentation for this. And I think I'm joined by Ben, who will be added later. So yes, so this talk has two parts. The first is about the tools we use, like describe how it works, and the second part is more like on a meta level, like what do we achieve with it. And so for background, most of the infrastructure in Google is proprietary and separate, unknown to the world. And that doesn't change going forward. However, there has been a push towards open source in general, and some of the lower level libraries have been open source because they were simply needed on the outside. And also teams are developing in open source now, many teams in fact, and Project Oak being one of them. So we are somehow in the middle between both sides, having our major source of truth on the open, but obviously things are needed internally as well, where there is no secret involved. It's just enforced by the dependencies we have. So the problem we were faced at initially, like 2 years ago when this started, is that we had binaries coming out from the open source repository, and they were needed internally, but there was no way to trust them. So there was no process. It had to be done manually, and so we built some tooling for this, and like this matrix here is basically on the internal means Google internal and external means open. So there are the source of the binary can either be internal, and where it's deployed is where the trust is needed. And so internal is clear. That's not the topic of this talk. Then we have internal binaries deployed externally. That's also out of scope for this talk. It's interesting, but out of scope. And the major focus is on external binaries deployed internally. And of course, it's a little bit weird. Why don't we have external? Why is this in brackets? It's not open sourced, but for no reason, or maybe for a strong reason, because we connect to the internal infrastructure, and we haven't agreed on a good place where to store the signing keys externally. So that's the only reason for that. Otherwise, we support external case by some detour through the Google infrastructure. So here are two binary blobs. I mean, they look pretty rogue, but they are supposed to be nice binaries. But I still like this picture. And so this is actually the same graph Hayden showed earlier. It's like a standard deployment pipeline where the last step is missing. So we don't consume in this diagram. And so the problem is we are Project Oak, or anyone using this infrastructure, and we have a binary, and we trust that binary, but we also want to convey this with everyone else. And running it through this pipeline, we first run the builder, and the provenance comes out of this along with a binary. And next step is assembling a package which contains a bunch of files. So the binary and the provenance are already there, and it adds a few files, and also makes one round trip to Record by adding the signature to the standard tlog place. And then we take these files and put them somewhere where they can be used later. And yes, so these are the 3 files we're adding. It's an endorsement, which we will have a look at later. There is a signature over it, and there is a log entry for the signature. So now a quick look at these output modalities. So the mainline output is to a repository. That's what we have been using right from the start. And it's very easy. You have the binary there, and you can just link it into any application you want and run it. And it can be also used as an archive if you really need to. But then we had some difficulties with large binaries. So when the binaries become extra large, then repository is not really an option. So there is the notion of MPMs, which is basically a binary archive tailored to Google infrastructure, which you can run directly. So that's kind of handy to put the stuff into an NPM directly without the detour to the repository. Next step of the evolution is cloud storage. That covers all the stages, all the cases where you need to refer to it from external sources. So it's cloud storage which is publicly accessible, but not listable. So you cannot see anything unless you have the hash of a key or a binary hash as well. And we have Rust code to drive the storage. And finally, disk storage is like whenever nothing is a fit, you can just write it to disk and then do something with it. I think I skipped one. Yeah. So this is the cryptographic core of it. It's not much, so it's disappointing actually. You can just assemble everything via standard tools. So all the files involved are mentioned here somewhere more or less. So the first is the generation, and the blue stuff is the consumption. And why is this not good? Why don't we do that? It's because the private key is on the local disk, and that kills it. So we don't want to have private keys flying around ever. Okay, so it's yeah, I think I said everything about this one. And now we had Holger and reproducible builds earlier. This summarizes our attitude towards reproducible builds. So we maintain two Git repos. One is Git repo source of truth, and the other one is on GitHub. And from every repo, a builder produces binary and provenance. First branch is called Kokoro. It's also some piece of infrastructure. And the second one is GitHub. And the source code copying happens via Copybara synchronously, you could say. So you submit, you merge something in the Git repo, and it instantly is transferred to GitHub. So we have 2 binaries and 2 provenances. So we just compare the 2 binaries, and if they're identical, then we simply declare this sufficient for the build to be reproducible. Yes. So the assumption is that a third time will work as well, and by corollary for everyone else who tries that, it would work as well. If it's not reproducible, then there are two reasons. Either it never was reproducible, then this is fine, this can be dropped, or there is a regression, of course. Then the CI is broken. So next, how do we consume? This is our, this happens to be open source code as well. Like this is a hardware-rooted container application running on AMD, on an AMD EPIC CPU. So, and there is a chain, like all the arrows between the boxes basically are one signature that is verified, going from AMD root key all the way to the actual binary you want to run in the TEE. And now this is a multi-step project process. So you first verify all the arrows, and then on top of that, we verify the endorsement packages for every single binary that is part of this of the later layers. There can be more than one binary in any layer. So for the kernel, I think we have at least two. And yes, what else is there to say? So this is a unit. You verify the endorsements. And the main upside of that is that you don't have to know the hash of the binary in advance. So these binaries change all the time. So you merge something and it's rebuilt and it's different, but it's always signed by the same key. So we can just verify using the public key and not the binary hash. So that makes it very practical if you have to store reference values on user phones, then you would just include the public key and it would be invariant to changes of the binary. So one slide about the external case. So that's pretty weird because we're just we are pulling that inside only for the sake of signing. So it's the only reason. And this works when you have stuff which is in maintenance mode. It's just need to be rebuilt, but for tinkering this is infeasible. And below is an example of how you would consume this from the cloud storage. Sorry, I should have spelled out the acronym. I hate this if there are acronyms in. So this is Google Cloud Storage, and this is an open source call which basically shows you all the endorsements made for this binary hash. There are also other ways to look it up. So once you have these coordinates, it will show you everything. If you don't have them, it will show you nothing. So now about claims. How is time? This is finally this is the endorsement format which we sign. It's a standard in toto statement with a standard subject, but only on the predicate side we roll our own. There are basically the only, but there's not much there, right? It's only like a validity, which is from to, and also the date of issuance is recorded and can be verified. Even though we don't do it, we mainly verify that the current time is within the validity. So this allows. So these things run out. They run out after. I mean, this is, I don't know, 3 months. Yeah, that's a standard duration. But we reproduce them all the time, so it's fine for them to run out. And also there are these claims, and I will go into the claims into more detail with the claims. So this piece of information is available during the TE attestation verification. Yes. So the relationship to claimant model is pretty straightforward, actually. So the statement is the endorsement statement, and the claimant is the owner of the signing key, which is the developer, but could be anyone who signs. The claims are variables. So there were these URLs for claims, and they just resolved to human readable text, which is like, I don't know, some legal language. You should be very accurate when doing this. And the believer is the person, entity, or infrastructure who uses the binary, or it's also pretty open. The action is also open, and the arbiters as well. So everything is possible, can be shaped as it can go from major loss of reputation, or like the other one, starting small from basically nothing to something really big and problematic. Yes, I think my time is, it's okay. So an example for our claims, for some claims we're having, is we have claims corresponding to our own transparency levels. So there are many ways to define transparency levels, and I think we are following several approaches. This is just one, which is not really leveled, so it's not layered, but it's just a flat properties of the binary. The binary is published, meaning you can download it from somewhere. The binary is runnable, so you can either directly invoke it, or there is like an additional environment which makes it runnable. Open source is, of course, source code, and all the dependencies are open source, and reproducible builds is clear. We covered that. So for each of these, except none, there was no claim for none, you would assign one or all, up to 4 claims to the endorsement. So so these are the 4 claims we're using for the transparency levels. There are no good claims, not really falsifiable. So what would happen if how could you break them? Maybe the source GitHub goes down, but then it comes back. Maybe. But then it comes back up again. And was this? Would you get sued for this? Probably not. Then a better claim is this no insecure logging. So a binary promising that it doesn't log anything. And finally, and with that, I'm going to pass it over to Ben. About we have a toy project which is really neat and is better at showcasing this. So
hey, hopefully you can hear me.
Great.
Cool. Hi everyone, I'm Ben. I work on Oak with Tom. So firstly, I'm sorry that I'm not listed on the schedule. This morning it was suggested that I present a couple of the slides in this talk. I had intended to be there with you at the conference, but unfortunately I couldn't be for unforeseen circumstances, so I'm here in sunny London.
We need a cardboard model for you, just wait for Martin.
Oh goodness, I hope not. Anyway, so yeah, as Tom was saying, in the Oak repo we have sort of a toy claim or a toy challenge around a claim, specifically a capture flag sort of challenge. So I'll go through it and explain it in a bit more detail. So it is, or the claim comes in the form of a binary that runs in a trusted execution environment. In this case, actually confidential space, which we learned about a bit earlier today. It's a very, very simple binary. You can go and look at the code. The link is at the bottom of the slide there. All it does is generate a random secret, calculate that secret's digest, then asks the runtime to create an attestation. In this case, it happens to be a GWT that is bound to the digest. So part of that attestation, the thing that's being signed over, is the digest of the secret. The binary then logs that attestation out so that outside observers can go and see the attestation, and they can go and verify that attestation against, well, lots of things, including confidential spaces, root public key. And then it discards that original secret, which, at least theoretically, unless we wrote some bad code, did not ever leave the TEE. As it happens, the binary, if you go and look at the code, is like artificially weakened to hold on to the secret for a few minutes just to give people an opportunity to attack it. But again, it should not ever leave the TEE. It should be safe from attack. So the claim here is that the secret, this random number that was generated at the very start, cannot be known. The way that you can falsify that claim is by presenting a secret and a valid attestation that is bound to that secret to the arbiters. Now the interesting thing here is that the arbiter, like, yes, is us, Project O, but actually arbitration is itself down to, or is I guess, evolved down to another binary which happens to be sitting alongside the claim binary, again, which you can go and look at the code for. And all that thing does is verify the attestation. It looks the way it should, was produced by confidential space, was produced safely and securely, and was produced by running our binary, and is bound to the secret that you provided. But if you manage to figure out the secret, attack the system somehow, and provide a valid attestation alongside that, this arbitration binary will tell you if you falsified our claim. And if you do that, please come and tell me, because I would really like to know about it. Next slide, please. So an idea that we have here is that one could make many such claims, many such falsifiable claims, ideally machine checkable claims in the way that I just described, with this kind of falsification checker binary. So you could make much of those claims and associate each one with some amount of money, forming a bug bounty. Any person could put a bounty on the claim, not just the code owner, right? So it so happens that Oak code, for example, is not just used by Google, it's used by other companies that might want to make claims about its safety and security, and so they might want to put their own bounties on it. As per the example here, so multiple parties sharing the same libraries, and you can imagine like even much more, common libraries used across the ecosystem. Obviously, the sum of that money is paid to whoever presents evidence of falsification the first time, not repeatedly. And what's interesting here is, like, if you start playing this out a little bit, you can start thinking about how this starts to look a lot like a financial market, and we know how to run those. Those financial markets are pretty good at being very efficient, and it'd be interesting to see how far you could go there in an effort to enhance security of these commonly used libraries. The principles here are that the bounty value is a measure of confidence of the claimant, also of the value of the claim that they're making to them, right? So, like, if you're depending on some library that underpins your entire product, you probably want to stake a bigger claim on that than, I don't know, something that's not that important to you. The reason being that higher bounty values will attract more effort. They'll focus attention on the library or piece of code that you want people to spend time falsifying their claims around. And so, you put more money down, you're likely to be able to strengthen that claim more efficiently. Anyway, back to Tom.
Thanks. So I'm continuing with two more slides about challenges and future and outlook. So what we did initially was we navigated through lots of choices and interfacing with the internal things. So we wanted to make something which is really usable, not only for us, but for other teams. And we had lots of discussions on what would be the right balance between special case and generality. And I think it worked out reasonably well. Another challenge was to pull through a rotation of signing keys, which is desirable, at least for recovering from disasters. You should have procedures to do that, but it can also be done routinely right now. The problem is, of course, if you hardwire a public key on the phone, then you can't rotate it because Android apps cannot be easily forced to update. And a third challenge was to navigate through protocol buffer changes, which are time-consuming, but safe because you have like rules that you can follow, and you're pretty sure that it works out. But we have one client where we wait for an entire year until we can remove the fields because they're updating their apps only every now and then, and so they want 1 year of wait time, which is a lot. So we have a lot of snoozed bugs around this. And future work, here's some ideas. Of course, as said, external tooling would be great, but this also requires to take into account what's there. Cosine is very close. Others as well. We've seen a lot of things which overlap in some way. The next is just vanilla use of Recore would be better to be on the forefront of all the T-log developments with that. Claim landscape and bug boundaries, what Ben talked about, that's pretty early. I skipped the details about managing changes of claims. Because it's over time. And also the question of external trust for internal binaries is interesting and worthwhile. And last but not least, what's up with attestations when combinations of many TEs in one system by whatever means. I think that's it. I'm over time, we.
That's okay. It happens. Round of applause to Tom. Do we have any questions for Tom? We do have time for maybe one or two if there are any. No? Well, if not, then we'll stick to the schedule and move on. I will introduce Billy to come and talk to us about Crescendo. Another round of applause for Tom. And Ben.
All right. Good afternoon or evening. Thank you for the privilege to be here to talk about the work we have done in Android ecosystem. I would like to share with you the various works that we have done to so-called increase the intensity of our efforts. I entitled it Crescendo. Just a brief introduction. My name is Billy Lau, working in Google in the Android security department, org, however you want to call it. My passion is really in transparency efforts right now, but in a more general sense, I like to make secure systems more usable and usable systems more secure. And this line of work, I think, really will help achieve that goal. Speaking of goal, I'll quickly outline this talk by saying that we'll start with describing what the final world that we want to look like, so that we know we know when we get there. And quickly, I'll recap the work that we've done for Pixel firmware transparency, which was entitled the Odyssey. Successively, I will point out the clear gaps that we have in binary coverage since the first work that we've done. Next, I'll talk about how we tackle complex continuous build test integration systems, one that is Google scale. I'll dive into some design and deployment decisions that have been made and how that leads to the next point of why actually automation is crucial for large-scale deployment. This will then help equip us to take on the big fire hose and take a peek at what's coming. So let's dive in. The primary objective of this entire movement effort is to provide a verifiable and auditable log of all firmware updates for Android devices, right? Ensuring that users could trust the software running on their devices. And this should extend to software running at all levels, from the bootloader to the kernel, to the OS, to the system apps, config tools, and all beyond. And why this is important, because obviously if things are verifiable and transparent, it builds trust in your software, in your product. And also, I like the property that it will help increase resistance to insider attack and coercion type of attack. So far we embarked on a journey many years ago. I forgot how long. And in the previous talk that was given in the first workshop on cryptography applied to transparency systems, or CAT, in 2023, I introduced our work on Pixel firmware transparency. And there's a GitHub link there that links to the slide for that talk on how a user can use a transparency log as a reliable source of ground truth for legitimate firmware. And that was obviously scoped to Pixel, starting the release from a specific device model. And obviously the journey had just started back then, and that means there's a lot of ground to cover, as we see here, before we reach the transparency. So where do we go from here, right? If we were to think systematically, then we'll come to the conclusion that every other binary that is updatable outside of a firmware OTA or firmware update it's all fair game. We should cover all that, and that is correct. But we can also make an observation here, is that a lot of things in Android are actually APKs. These are apps are APKs, system apps are APKs, and so on. There's just so many of them, but where do we start, right? It seems to be a good idea to start with kind of like the most privileged level, like system APKs, right? Since they have a lot of privileges and often handle sensitive user data. So, and that's our strategy, right? Existing production pipeline for existing binaries and apps are actually so established now, and it's operating at its own pace. It's not to say that we shouldn't try to tackle that, but to start with that right away, I think it's a tremendous challenge. And if we take on that and don't expect any disruption to that, I think it's like daydreaming. So, but if we know Android well enough, we know that like every once in a while it'll come up with something new, and that's precisely the next strategy, is to choose a new class of apps and let's try to hook into that release process, since they are going to kind of start anew, right, with our binary coverage. And then I struck gold. The internal team has decided to launch a new class of APKs called the Google System Services APK. And it happens to cover two packages called Safety Core and Key Verifier. And for those who were monitoring Android at the time, you may remember that one day suddenly these two apps start popping on your device. And thankfully, we have transparency logs for them. And so I went to work. I studied how the new app is being made, get to know the CI/CD environment inside Google. it's kind of like studying how sausages is made. Learn about where the various build artifacts are produced, where they are signed, and then when they are put into secure storage, and when they are ready to go for distribution. And yes, I found it. I found the right place that I think to intercept the process, and then so that we can get the artifacts, measure that, write that to the log, problem solved. Thank you, I'm done. Actually not, right? If only things were that simple. So it turns out that at the end of 2021, Google Play no longer takes APKs for this distribution. It introduced another form of file format called the AAB, or Android App Bundles, which is supposed to contain all the things necessary to build the APKs. And then at the distribution end, based on user-specific configs like screen density, dimension, language, whatever, it would create a customized APK, right? And then from the AAB that was uploaded to Play. And then it will sign the newly created APK with the developer's keys and distribute that. So in other words, you kind of get a personalized, customized APK. So if you go back to the sausage analogy, it's kind of like shipping all the final ingredients and casings to the supermarket, and the sausage that you buy is kind of like a custom one, but it's being packed at the supermarket on demand and then sealed with the manufacturer's packaging and then sold to you. So that was quite an abrupt change that just have to adapt with that for this work. So at this point in time, you think like, why don't I just tap into Play, since Play knows what the final file looks like? And the problem here is that Play is such a huge fire hose, and at that level scale, and Play is basically distributing everything, right? Not just Google first-party apps, but every single app in the whole wide world. And I don't want to break things to start with, right? That would not be good, especially if we want to if you want to play nice and have people buy into, getting transparency. So I will have to back up the pipeline a bit more and work with what I have. So the idea here is like, let's find something that's unique that we can fingerprint, right? So although the AABs are not the final forms of binary that is shipped to the end user, it certainly has to be the superset of all the ingredients, right, that's delivered, because things are taken out and customized by right. You shouldn't add new things into the APK that is not already in the AAB. So something has to persist across the transformation. So the quest here is to look for what that thing is. All right. So, and thankfully and rightfully so, the code does not change, right? In fact, it should not change when AABs are transformed into APKs, else we would effectively have an app marketplace that tampers with developers' code, and that would be quite unacceptable. So I was finding a way to fingerprint the code in each package and app, and the good news is that when Play introduced AAB, they included the ability to sign code. So this is good news. And essentially, this diagram shows kind of how the code signature would work. And it is in the form of a JSON Web Token, or JWT, that basically lists all the codes in your initial produced AAB, which will then go to the APK file. And the idea here is that the developer will hold a separate set of key and sign this token, and then build the AAB and upload that to Google Play. And Google Play then, on the blue side here, hold a separate key, also developer's key, and then package that and send that to the user. So at least with this now, there is a way forward. I don't have to reinvent the wheel on, creating custom process to fingerprint the code. So I can basically just use this, and there's tool provided for that, which is called Bundle Tool. And if you're a developer, you can actually make use of that. If you so-called don't want to fully trust Google Play, you can sign your own code, and you can check this at the end when it's distributed to user device. You can pull this out and check to see that everything matches. So even though the process is new for this new app, but it's actually built on top of existing infrastructure, which is legacy. And when you talk about legacy systems, you know that there's going to be challenges and frictions. And since, thankfully, that now I have an understanding of how things move around, I realized that there's still a lot of manual labor. And the answer to that is to work with a group of engineers called release engineers. They are like the last humans in the pipeline whose job is to ensure that app release happen correctly and smoothly. So the idea here is to go to them and tell them like, hey, whenever you are releasing this app, please run this new script. And this script will take care of processing the artifacts and writing to the log, as long as you provide the correct parameters. But because of there's still complexity for that, we have to develop a playbook so that they can follow exactly. They don't have to improvise. We don't want to introduce errors. And that is actually very crucial in the process to make sure that every time this manual process is triggered, it is a deterministic process. So with that, a new transparency log is born. And please refer to the link there for more information, or you can just Google System Services APK transparency log, and there's a whole description on what it is, what is covered, how to verify them, how to pull APKs from device, and get to that code token. So now I'm going to step back a bit, and we can talk about what is next, and we can see that there's so many more other binaries that we're looking to cover as we increase the intensity of our work. And you see that, it kind of makes sense that if we can cover things that is relevant to the current AI hype, the file configs, AI models, or custom sandboxes. But these are like ambitions. How do we get there, though? And this is the moment you realize that you just cannot perpetually add more manual processes and hope that a new type of class pops up and then you just add that again. It's just inviting trouble. I think it's a good first step to try to test the water to see if things work. And not to mention with this manual process, each time a release happens, there is a moment of heart attack because there's always this possibility of human error when it comes to manual processes. So it should be clear, hopefully, now that the real answer to what's next is to build automation. And there are different stages with automation, and it is crucial that we identify each dependency at each juncture of the release pipeline. Because, as mentioned, we're dealing with legacy systems. You cannot just build all different automations and just apply it and turn it on at once and expect things to work, because things usually don't work the first time. So planning ahead is actually very crucial. And with a little bit of power of hindsight, my advice to other practitioners is that actually, whenever possible, if you want to start transparency efforts, you would want to start with automation, even though you may pay a bit of a higher price, higher in terms of effort to get it done. But you want to start with that because then you can start from a clean slate. You can start having your automation write to a completely new log, which if there's any errors, you can discard it and then publish it when you've weeded out all the errors. Just generalizing, what are these challenges, deployment challenges with automation here, is that because now we have a manual process in place, and we want to switch that to be automatic. At least that's the case here. And the challenge here is that it's not as simple as it seems. And just to recap, at this point, we still don't have access to APKs yet. And all the dependencies must be managed very, very carefully, especially the order of dependencies. And one aspect that is not to be overlooked is how important cross-functional collaboration is. And good communication is essentially key. You don't want to surprise your partners who want to help you in this effort by, creating unintended artifacts, and then they will have to try to figure out what was wrong. You want to try to make it as easy as possible for them to adopt your new solution or automation. So, and one that is particularly pertinent to transparency systems is that errors are unacceptable, right? Even though I claimed earlier automation is the gold standard, we need to be extremely careful and precise in our execution of creating and deploying automation, because we really don't end up in fatal errors that would kill the log. Don't want to end up to be a statistic like the talk on the first day. So key observation here is that, unlike with the brand new log, like I mentioned, there's no direct way to stress test your automation before just like unplug from the manual and just turn on the automation. So in this sense, you really have to trust the unit tests that you've written, and other kind of simulatory integration tests that you've written, and hope that they are comprehensive, and really run those tests with all possible scenarios. And this is, in fact, what we are currently facing. Because after you build and deploy, you are ready to so-called integrate into the other systems, legacy systems here. So obviously the correctness of data is very, very important. In the manual case, you actually have some advantage in the sense that you can actually pick up the binary for inspection. You can check it, and then before you actually commit that into the log. But in automation, once you switch over, you don't have the luxury of doing that. You need to be really 100% confident that the code handles all the processing, marshalling, unmarshalling of arguments, and it would just have to work correctly. And but before you reach 100% confidence, how do you validate your automation, right? And secondly is the signing operation, because when you write unit tests and run all the tests you don't have access to a production key, and that is by design. You really don't want to misuse your production key. So essentially, you don't know what will happen when your thing actually makes use of production key, and make sure that the parameters are set accordingly that your production key, when it is used, is to only sign production log, which will then be published. And lastly, the export operation is basically the operation of reading from the log and exposing that to the outside world. There are some assumptions that are made with the initial manual process that we later on find out that we are unable to fully bypass that in time with automation. So it's things like that which we should be careful of when we first introduce even a manual process that we later think can be fully automated. So as of last week, the latest entry to this log as pointed out here, I'm happy to announce, comes from fully automated process. And again, you can refer to the link above there, which actually points to all the leaf nodes that we have. And while we're here, I'm going to give a brief introduction to what this each entry of this log means. The first line is the hash of something, and the second line tells us like what is that hash about? Is the hash descriptor? And in this case, in most cases here, these are the SHA-256 digest of the JWT token, and the third line is the package name of what hashes this corresponds to, and the final one is the version code. So as you can see, all the updates to the same package should have increment in terms of version code. And so from now onwards, I'm again happy to announce that we have successfully dismantled all the scaffoldings and moving forward in a fully automated manner. And we are ready to take on more with this. And so it's time to actually talk about like what's next in terms. So besides just covering our expanding our coverage to other binaries such as like AI models, configs, or whatnot, we are actually also exploring other creative usage of data that leverages transparency constructs. One of which I'm quite excited about is to be able to make a claim about how common a build is in order to protect users from targeted attacks. The idea here is to try to leverage the data we have from the initial key provisioning, attestation key provisioning step, without getting into the full details, to make statements with confidence about like which build we know are widely installed. Then if we surface the information, you can imagine that you can use that to build confidence in knowing that the build that that was given to you or that you've downloaded was not like a particularly targeted build, so to speak. So, and also tangentially, we're actively exploring the most efficient way to add verification mechanism into the Android framework that would allows us to inch a step closer to the end goal that we wanted to get to. So I kind of blazed through all that, but yeah, I'll end there and with questions. Yeah.
Any questions for Billy? Yes.
As I understand it, this is proprietary thing, so you can't have third-party rebuilders. But do you do any internal rebuilds to verify that the binaries match the claim source code?
Yeah, so the claim we're making here is a more specific claim in the sense that to say that only things that are recorded in log are so-called legitimate binaries. So does that first answer your question, or in the right direction?
I mean, you get consistency of what the release binaries are, but do you make any claims verification that the binary that appears in the log corresponds to the expected source code?
So you mean, is there anything internally that corresponds to that? The short answer to that is that we don't do this reverse correspondence. To my understanding, not all of those are like reproducible builds to begin with, and secondly, it's we trust on the tooling and the what do you call that? The surrounding echoes on the tooling and the build pipeline to ensure that it cannot be tampered with. And as I understand it, some of these build pipelines has had external audits to satisfy some different certifications but I'm not super clear on the details of that, but that was my rough understanding of that.
I was wondering, have you considered using public transparency log for your purpose? I mean, even if the data itself, you don't want to reveal it, but you could log a hash still?
You mean like making use of SIGSOR and stuff? Yeah, that was the kind of suggestions that we've had before, and we like to have control over like the availability of the log that we have for the final goal. Where if you think that I forgot if I mentioned this, but if you think of a world where we want to be where to say like I'm not going to install this binary or update this binary unless it's in the transparency log. So you want to have high availability and reliability of the log, and to some degree having that within our control, the purview of ourselves makes that slightly easier to control.
So there are 2 transparency logs at the moment. So would there be any client-side verification automatically, or?
Right. So the client-side verification is the one that I'm alluding to, where we want to get to, which is the next step. As I mentioned, like I'm looking to find the most efficient way to, with the right level of semantics, to incorporate that kind of logic into the operating systems. So we don't have that right now. What you have is steps to kind of convince yourself that the binary you have is actually, the binary that is transparent. But that's where we want to get to.
Right. I think let's thank Billy again. And I'm going to invite Tiziano to the stage for our final talk of the day. Better make it fun.
Hi, everyone. Last talk before dinner. No pressure. I can feel the energy. So I'm Tiziano. I'm the engineering lead of Project Oak. I think you heard from a few of our colleagues today. And today I have 2 goals. I'll keep it short. I have 2 goals for this presentation. And it's about to tell you about content addressability, if you don't already know about it. It's a pretty cool concept. And I'm going to tell you about end and static space, which is some of my projects. But first, I have a task for you. I have a shopping list. So if you can help me go and do this shopping. Spoilers, this is a location-addressed shopping list. So you have to go to the supermarket, and then you get to the aisle number 3, and you go to the 4th shelf, and you get the second item from the left. And then, whatever. You can see the rest there. What can go wrong with that, right? Imagine that you actually have to do this thing, right? I literally give you this list and tell you where to go and where to find the items, right? What can go wrong? 404, maybe you go there, the supermarket is closed, doesn't exist anymore. Or maybe it is open, but you go there and on the 4th shelf of the 3rd aisle, there is oil instead of the milk or whatever. Or maybe the items are there and you go and fetch a box of crackers, and instead of being like a nice square box, it's like all like broken, and the stuff inside is not that good. And finally, if I give you this list and you go to a different supermarket, this list is completely useless, right? So, I mean, I know this is a silly example, but if you think about it, this is kind of like how most of the internet works today. If I give you a URL, if you really think about the pieces of the URL, right? It tells you what protocol to use, which web server to go to, and then the path inside the web server that you need to access a file, right? It's really how it works. And so think about it if I give you a list, I wouldn't give you that list. I would give you the content of the things that I want you to go and find, and then you figure out which supermarket you want to go to and wherever they are in the supermarket, right? It doesn't really matter to the extent that I give you the list, right? But yet we seem to accept the previous model, the location address model, is fine for the internet, while this is a content address version. Has some advantages, right? So I'm going to tell you today a little bit about end, which is my one of my sort of side projects. It's a Google project, but it's not an official Google product. So please talk to me before you actually take a dependency on it, if you ever consider that. Really, basically, the idea of Ent is just is a protocol that lets you resolve, like given a digest of whatever binary, it tells you where you might find the corresponding files over the internet, giving you a bunch of HTTPs. I won't go into too much detail. I don't have much time. I'm happy to talk more or take questions about exactly why it looks kind of weird like this. But you can imagine, basically, you have this protocol, and I'll show you how to run a server. It's open source and stuff. The server, I'm in the middle of migrating from a different API to this API, so maybe some of the examples you'll see in the repositories are a bit inconsistent, but you imagine you do a HTTP GET request, which contains the digest, all of it. It has these folders because you don't want to sort of like just have billions of files in a single folder if you were serving this statically. And what you get back is some JSON with some metadata. The metadata has stuff like the size of the blob that you're going to fetch. The content type is just is nice to have. All the other digests, like maybe SHA-256, SHA-512, SHA-1, SHA-3, whatever. It has more than this, of course. And then the important part, you have a bunch of mirrors. The mirrors are just places in which that binary has been seen before over the internet. And there's also a hint whether each mirror is compliant with CORS or not. So if you're fetching it from a browser, you know whether it's going to work or not. That's basically it. It's just a standard, like this is the standard more or less. It's specified in the repository. If you think about it, it's pretty useful already. In addition to the server, I also have a command line client, which looks pretty much like this. And you give it the thing you want to fetch and where you want to save it. And basically what it's going to do is going to go and fetch these mirrors. And I have an example here. There's maybe 2 mirrors in this example, and it goes through both of them. And the important thing is really it must check the consistency is correct or whatever it goes and fetch. It doesn't just blindly download stuff from this mirror. So in this example, it gets 2 mirrors. It goes to the first one, and the first one doesn't match. So it just keeps going, goes to the second, and then the one matches. So and then eventually you get the file, which is a PDF in this case. So pretty simple. And the command line tool is written in Go. And you will see that there's a lot of integrations I would like to do with a lot of the great stuff that you all here are working on. So Ent servers are untrusted, which is good. You don't want to have to trust such a server. The point is that if you are a client, then you rely on Ent. You have to verify the digest locally before you actually accept any content from any of the mirrors. They are lightweight because they only store metadata, really just the JSON for each digest that I show you. It stores the JSON, it needs to serve the JSON. So the storage and the bandwidth is very, very cheap. It doesn't store the actual data. It can be run statically. Now it doesn't work quite like that at the moment if you go and download it, but it does. It will support static serving soon, inspired by Tessera and Sunlight, of course. And anyone can run one. Although I don't really envision that would be a ton of these servers. You can think of these like DNS servers. Like you're not going to run your own DNS servers, right? You're going to have a few of them out there that are good to use, and you're going to use one of those. And probably we need to have a few of them, but not one, but like not 1 million probably. So actually, there's a couple of instances here. One is the first one is just a GitHub repository, which is basically just statically serving an index, which is work in progress because I'm changing the API. And another one is this website called Static Space, and yes, .space is a TLD, which is pretty cool. So this is the server that I run for public good. It's very cheap to run because, as I say, it doesn't really cost much to serve these little bits of JSON as a web UI. You can try now. If you go open your browser, you type static.space, you actually go to this website. Please don't break it. You can think of it really almost as a URL shortener, except it makes the URLs longer because the URLs are pretty long. So you can actually stick a URL of some file that you have in your S3 bucket or wherever. You can put it literally in the search box, and it will index it, and it will give you a URL with the digest, and then you can send the URL to anyone. And really what it does, it's a pretty easy way of preventing split views across time and also across clients. If I send you a link to anything, going back to the analogy with the location addressability, if I send you a link to like a Wikipedia article or a file or a PDF or whatever, First of all, there's no guarantee that you're going to see the same file that I'm seeing. It could be a completely different file, or maybe over time the file disappears and all the analogies about before. So we found that this is pretty useful when referencing things like manuals or papers, or like if you have a tweet and you want to refer to something, you want to make sure that everyone has the same view of the thing that you're referring to. If you're endorsing an article or something, having the digest in the URL, it actually does the trick. Or you have a repository and you want to point to a very large file, but without adding into your repository, you can use it the way. And they basically, philosophically, I think there is an interesting analogy. I think Hayden talked about package managers and so on. There's a cool sort of separation here. You can think of a lot of these things here as sort of like mutable pointers, and you can think of a package manager basically mapping the name of a package and name and version to a digest, and then you can completely separate the storage. Once you know that like a version 0.1 of some crypto library, whatever, resolves to a digest, then where you get the blob corresponding to the digest is completely different problem. There's no reason to mix them together as they are in most package managers today. So this sort of gives you a nice way of separating the mutable pointers from the immutable data. So a bunch of future work. If you take a look, a bunch of stuff is broken, but I would encourage you to let me know if it sounds like something that would be useful to you. And if you want to play around, it's very simple to run a server and also a command line tool. And I give you the link to the static spaces, the web UI. Take a look around. Thanks for the feedback, and thank you.
Am I on? Super speedy. Any questions for Tiziano? Go on.
Dinner.
So I was wondering about the way this thing gets populated with data. And you mentioned it can happen by someone entering your website and they type in the stuff. Could it be populated in other ways as well?
Yeah. So now it's pretty manual. You can go there. There is also an API actually. So if you have like 1,000 files, you can do HTTP requests to my server, and it's just going to scan each of them and populate it there. I'm thinking of other ways as well. Maybe you have a trigger on your GitHub Actions pipeline that for everything you publish, you sort of just trivially is going to call into it. I'm trying to convince people from GitHub to maybe do this automatically in some ways. But so far it's pretty manual. There's an API. You can mix and match. But let me know if you have ideas or you want to use it for something else. The API is not batch, but you have to call it once per item. But so maybe a batch API would help some use cases.
Yes, thank you for the talk. I'm going to come after you after the talk because I think we are building the same thing. I'm
surprised no one has built it, actually.
Me too. One problem is I think the thing is useful if the index is built by someone and who may build a very large index of that and who will certify that the mirrors are not spam, for example.
As I mentioned earlier, I'm really keen of the fact that the survey is untrusted, so I don't want to have to trust it. The point is, of course, you would accept some level of spam in the mirror, so that's why for the client it's important to check. That's why even in the hints, in the metadata, I have the expected size, so that if you get a malicious mirror, then instead of sending you back like the 10 kilobyte file, it sends you like a 10 gigabyte file. You're gonna just truncate it and just not even bother with it and just go to the next mirror. So there's some heuristics you can apply to limit the spam. And then as the operator of the index, if you detect that one link is spam, you can just remove it, of course, from the mirror. You don't need to keep serving it forever. But obviously, in some cases, it might be harder, right? Maybe it's the same URL based on the user agent. It resolves differently, or in different countries, or whatever. So I don't think it can be eliminated. But I think there are interesting things that we can do to limit the spam. So if you have ideas, by all means, let's talk about it. 1, 2, 1.
Yes. How would you handle a hash collision? I know it's very, very unlikely, but let's suppose it was possible.
I don't do anything special with it, but I do have multiple hash functions. So for each file, I index according to several ones. Now there is a primary one. I don't remember currently if I use SHA-2 512 or SHA-3 512. One of them is the primary one, and the other sort of like points to that one. So in some cases, if there were an hash collision on the SHA-1, as we know that there is, you would notice. Now the API doesn't make it obvious, but you could get multiple entries. And now I'm assuming that one of the hash functions at least doesn't have collisions, which might be falsified at some point. So let me know if you have ideas.
When you access a mirror, and let's assume the mirror is not malicious, but it may or may not have the right version of the data.
Yeah.
Are there any features in the HTTP protocol that lets you ask, I would like to have this file and I expect to have this hash, and if it is unlikely to have that hash, I don't want to download it?
That's a great question. I'm not an expert. I'm sure some people here would know, but there are some caching mechanisms by which you can have e-tags or something and say to the server what you expect to download. And also more specifically, if the target is an S3 bucket, I think there is even more stuff that you can pass in some headers to say exactly what you expect. But I don't think there is something sort of super standard like HTTP standard. But let me know if you know of anything, of course.
Okay, I think we'll leave it there for now. Thank you so much, Tiziano. Let's say thank you again. I think you did a great job bringing the energy. Okay, so that is it for day 2, in this room at least. A couple of logistical things about this evening. The booking for tonight is at 6:30, which is not very far away from now. I have sent a maps link and an image with the walking route. It's really close. It's that way, I think. Yes. But what we will do is we can meet as a group down in the lobby, aiming to leave at 6:15. I will be there, and Annalie and Marie will be there, and we can do sort of a group walk up. The map and everything is in there for anyone who comes a bit later or isn't in that group. If you don't happen to be on the Slack, I believe the link to the restaurant is also on the schedule that's on the website. So if you need it, and if you really can't find it, message me. I'll keep my phone on, and we can make sure you get there. So that is for this evening. And then tomorrow, I believe the schedule says, I've actually checked this time, the schedule says me welcoming you at 9:20 with the first talk starting at 9:30. Let's just say we'll start at 9:30 because I don't anticipate having to talk for 10 minutes first. So let's say we'll start at 9:30 tomorrow morning. Okay, let's go to dinner.